Hello everyone, I'm Mipen from Hunan University of Science and Technology. The topic of this presentation is Web Service Classification based on Graph Attention Network. And it is divided into 4 parts: background and motivation, research method, experiment and results analysis, summary and future work. The first part is the background and motivation. Web service is a kind of technology which can effectively carry out distributed computing and data integration. The API we often talk about is a typical web service. According to the statistic of Programmer Web, as of September 2020, the total number of web APIs and mashups is nearly 30,000. Basically, the number of APIs doubles every 2 or 3 years. For developers, how to quickly and accurately select the required API is a challenging task. Fortunately, we can use service classification to greatly reduce the time and space cost of web service search and discovery. The traditional method is merely based on the content similarity calculation of descriptions. However, there are some problems such as sparse features and ignoring structural information. Recently, some graph-based methods have achieved better classification results. But this method focuses on graphs only, or cannot distinguish label information of service where. In order to solve this problem, we use a attention mechanism to aggregate the neighbor services, and use deep neural network to update the representation of services. So, the content information and structural information of the service can be well combined. As shown in this figure, graph convolutional network calculates the preference value of different neighbor services by the degree of each node in the service network. For example, the weights of neighbor services send out, high write, and talent bin, calculated by the formula to the center service leaf work, are 0.4, 0.3, and 0.4 respectively. While it is obvious that the service send-out and high writes are consistent with the category of leaf work, but they have not received good attention. The service talent bin has a different category from leaf work, but it gets similar weights to high send-out. If we use the attention mechanism to parameterize the weights of neighbor services and adjust the parameters continuously during the training process, the final learning parameters can well represent the importance of different neighbor services, which is conducive to web services classification. The second part is our proposed method. The framework is shown in this figure, which consists of 4 parts: data pre-processing, service similarity computation, graph attention network, service classification. We first grab the web service from the network, and then through word segmentation, removing stop words, stemming processing, and related information extraction. We finally get the description information of the services, tags, and mashups. Then, the feature matrix and the similarity matrix are obtained by calculating the information from pre-processing. The two matrices are used as the input of graph attention network, and self-attention mechanism is used to aggregate the features of web services. Finally, the softmax function is used to predict the categories of web services. Next, we will focus on the second and third steps. The second step is the construction of service relationship network. It merely calculates the service similarity according to the two characteristics found from the service information. Service composition relationship, that is, two services called by the same mashup may belong to the different categories due to their complementary functions. Service sharing attention relationship means that two services annotated by the same tag are more likely to belong to the same category due to the functional similarity. Specifically, the cutting coefficient is used to calculate the similarity of shared tags between services, and what true weight is used to obtain the content similarity of two services. We adjust the weights of the two similarities to get the best results, and then the edge between the services with composition relationship is removed when the relationship graph is formed. In the third step, we adopt graph attention network to learn the network embedding of web services, and the specific framework includes 4 parts: input layer, linear layer, attention layer, and output layer. Firstly, the initial feature is discrete and high dimensional, and its dimension depends on the number of feature words extracted by word to weight. Our goal is to optimize it and learn the continuous and low-dimensional event vector. Next, we adopt a linear learning process to transform input features to high-level features. Then, we input these features into the attention layer and employ masked attention to calculate the first-order labels of each service. We concatenate the send services feature and the name services feature at the same query and key so that we can learn the word dependency within the concatenating vector and automatically capture the correlation between the send service and the name service. We concatenate the features of send service and the name service together, then multiply the concatenating vector with the weight vector to get a attention scalar. Finally, we use softmax and liquid value to get the final attention coefficient. Then, the weighted sum of the weight vector and the neighbors feature is used to obtain the new feature of the send service. At the same time, in order to stabilize the learning process of self-attention mechanism, we adopt multi-head attention to make several calculations. For the aggregation of multiple representations, there are different ways such as cascading, weighted average, and so on. At first attention level, we can simply get the embedded vector by concatenating without additional parameter learning. In the output layer, the final embedded feature is obtained by using the average value of multiple calculations. In our experiment, we crawled over 15,000 web APIs from the programmable web. We used recall precision and micro F1 as the evaluation indexes of the experiment. Deep work, not-to-weight, line, and graph convolution network were selected as comparison methods. It can be seen from the experimental results that the proposed method is superior to all four baseline methods in terms of precision, recall, and micro F1. As of the deep work, not-to-weight, and line, the classification result of our method is obviously better than the three methods using only a single structural information. At the same time, it can be found that when the number of service categories is small, such as 10, the classification result of graph convolutional network is similar to that of our method. However, when the number of service categories increases to 20 or 30, the classification result of our method superior to that of graph convolutional network. This is because as the number of service categories increases, the structure of graph becomes rich and complex, which increases the difficulty of service classification. While our method utilizes the self-attention mechanism to calculate the contribution of the neighbor services, which is completely dependent on the features of services and can be independent of graph structure. We make use of TSNE to visualize the classification result in our proposed method and the four baseline methods. The top 10 categories with the largest number of services are adopted in the data. We use the node colors to represent the categories of the services and reduce the dimension by TSNE to obtain the location of services. As can be seen from the figures, the service classification results of our method are generally better than the net 4 baseline methods. Here is the last part. In this paper, we proposed a web service classification method based on graph attention network. It adopts self-attention mechanism to calculate the features of services to identify different contribution degrees for different services in neighborhoods, and determine the category of service according to the influence of the first-order neighbor services. The experimental results on real datasets verify the effectiveness of the proposed method. In the future, we will consider to extend our method to include the features of age and We will consider focusing on the construction of service heterogeneous information network. Thanks for listening.
morning, ladies and gentlemen. My name is Nana Song. Today, I would like to report my paper that published in Proceedings of EAI 2020. The title is A Novel Multidimensional Comments and Co-Preference-Aware Recommendation Algorithm. The co-authors of this paper are Professor Yanmei Zhang, Professor Xiaoyi Tang, and Professor Huaihu Cao. I would like to give this talk in 4 parts: introduction, the MCC algorithm, experiments, and conclusion. The part 1, introduction. In the past, when I chose the same type of clothes on Taobao, the store name, reputation score, service attitude, product comments ethic are all factors I have to consider. Among them, I value product comments most, which can help me to choose products with better reputation to reduce risk. From shop A to shop K, I choose shop A because of its relatively good quality. However, in order to make profits, some businesses will invite dedicated personnel to review price. This makes product comments fail to fully reflect the emotional tendencies of customer groups. Clothes with good comments will still have problems such as color differences and poor quality. In real life, multidimensional comments show the scores of different dimensions of each product represents the user's group wider, and this group head modifier can be used to represent these products. Taking product 1 as an example, its head modifier relationship pairs include quality good, delivery fast, logistic fast ethic. Based on sentiment analysis, the score of each dimension is obtained, which can reflect the emotional bias of group users and help make better choices. Co-preferences relationship reflects the closeness between users, and their preferences are often similar. I also often browse the products recommended to me by the platform and use these products as an alternative for my shopping. Since the MCC algorithm, I can recommend products that have a good reputation and satisfy my interests. However, so far as we know, all-level approaches considered both multidimensional comments and co-preference aware, and there are still some problems left for these state-of-art approaches. The one is recommendation algorithm based on comments, which digs out the user's concern from the comments and adds them the preference model to achieve product recommendation. That means the characteristics of different users. There are still problems such as insufficient reflection of user interest differences. The other is the recommendation algorithm based on co-preference relationship, which adds the co-preference factors into the recommendation model and uses the behavioral preference information of the co-preference users to achieve the recommendation for the target users. However, there are still personalized recommendations, such as the single emotion of the users in the co-preference relationship. Part 2. MCC algorithm. In this paper, a novel multidimensional comments and co-preference aware recommendation algorithm is proposed. This is the framework of MCC algorithm. The upper and bottom rectangles with black borders are the offline and online process, respectively. The arrows represent the algorithm follow, and the hollow arrow on the left represents the updating process of user product rating metrics and comments. In the offline process, dependence relations in the form of head modifier are mined from comments. Next, the head words are clustered and the rating of every cluster with modifier words is calculated. Finally, a comment rating of each product is generated based on the comment. In the online process, when users enter the system, the co-preference relationship set of the users is obtained based on the pairs similarity of their historical ratings. Finally, users' ratings for products are predicted in order to recommend for users. Our experiments aim at addressing the following question. Question 1. How to select the cluster number key of key-means? Question 2. How to select the threshold of co-preference relationship? Question 3. How much does the ratios of chain sets and test sets affect the algorithm performance? Question 4. How does MCC perform when it runs on two data sets of different size and severity? The dataset we choose is Amazing Audio Equipment and Amazing Book Comment dataset. Evaluation metrics are MAE and RMSE. Experiment algorithms are random, contrast, HFT, SVD Jaja, Trust SVD, Trust MF. This experiment answers question 1. Figure 4 shows that the range of the best cluster numbers of 100 products is between 3 and 10. Different key values in the range are taken in the following experiments. We choose 80% of the data as a training set and the remaining 20% as a test set. The results are fundamentally the same in other ratios of training set to test set. The parameters in the experiment are set as following. Lambda d equals 1.2, lambda t equals 0.9. The learning rate is 0.0005, and the number of iterations is 100. Figure shows that the distribution of MAE and RMSE in the number of clusters is approximately the same. The MAE and RMSE of MCC are minimum when k equals 7, which implies that k equals 7 is the optimal uniform cluster number and should be used in subsequently experiments. This experiment answers question 2. The MAE and RMSE of MCC with co-preference relationship in different similarity thresholds are shown in tables 4 and 5. The setting of ratio of training set to test set and parameters are the same as in experiment 1. This is experiment equation 3. In the selection of clustering number in MCC algorithm, k equals 7 is selected as the optimal clustering number. The performance of MCC algorithm in terms of MAE and RLMC under the two data sets in showing figures 6 and 7. This experiment answers equation 4. The performance of the common trust SVD algorithm is compared with classical random algorithm as well as state-of-the-art algorithm, including common trust, HFT, SVD++, trust SVD, and trust MF by calculating the MAE and RLC. We set k equals 7 and the threshold of Pearson similarity as 0.9. Other setting parameters are the same as in experiment 1. The results are shown in figures 9 to 11. Compared with the baseline algorithm, the MCC shows certain improvements in terms of MAE and IMC. Compared with trust SVD and trust MF, the experimental effect improved by nearly 7.2%. Compared with HFT, compared with the baseline algorithms, the MCC shows certain improvements in terms of MAE and RLMC. Compared with trust SVD and trust MF, the experimental effect improved by nearly 7.2%. Compared with HFT, considering both comments and co-preference, the experimental MCC uses the multidimensional comment information and products to fairly alleviate data disparity. Moreover, compared with trust SVD, MCC directly replaces the average rating and the item dividation in trust SVD with a comment score that reflects the characteristics of products, which reduce the errors in the interactive calculation process, improve the accuracy of recommendation, and fairly alleviate the data disparity. The Part 4 Conclusions. The main contributions of approach are as follows. First, the MCC recommendation algorithm is proposed. It mines users' comments from multiple dimensions and co-preferences relationship so as to get effectively recommendation results. Second, experiments were conducted on two real-world datasets of different size
my pleasure to be here. Hello, ladies and gentlemen. My name is Jinglin Su, a master from the Central University of Finance and Economics. Today, I would like to report one of my papers that published in Proceeding of CollaborateCom 2020. The title is A Deep Recommendation Framework for Completely New Users in Mashup Creation. I co-authored this paper with my teacher, Yanmei Zhang, and Professor Shiping Chen from Software and Computational System, CSIRO Data 61. I would like to give this talk in 5 parts: introduction, related work, LDB, experiment, and conclusion. Web mashups are web applications developed using the contents and services available online. Compared with traditional developer-centric composition technologies, such as BPEI and WSCI, Mashup provides a flexible and easy-of-use way for service composition on web. Both the B2C business model and massive service information bring new challenges to service recommendation in the process of mashup creation. First, there are lots of new users without any service invocation records. Second, some service mashup platforms like Programmable Web store composite service information instead of any history of user invocation, so that which the corresponding historical data are quite scarce. Now, the types of service recommendation models are increasingly diverse. First, some methods usually use neural language processing technology for demand matching. Second, some methods mainly deal with original matrix and expand the original scoring matrix with implicit feedback. The third type of methods focuses on the relationship of user service. So, how to describe the complex relationship and make the model more suitable for new users becomes an intractable issue. In this part, I will introduce the related work in the early stage of our research. According to the recommendation algorithm framework, our related work is divided into the following 3 categories. First, we analyze some NLP methods such as LDA, walk-to-vec, and dog-to-vec. After continuous improvement, LDA has become one of the most classical text analysis models. So we chose LDA model to extract more accurate features of the text. Second, by search some methods focusing on matrix, especially Rundle combined the BPR with matrix decomposition technique and key-in for recommending. This method optimized the original matrix by increasing the probability of user preference and provided an important idea for 0 to 1 matrix decomposition in this paper. Third, methods focusing on relationship provide valuable ideas for our framework design. In conclusion, the methods focusing on the requirements matching by NLP can better mine user demands. Focusing on the original matrix can effectively elevate the cold start problem, but this method could not accurately mine the demands of users. Focusing on mapping relationship can learn the relationship more accurately, but it is easy to fall into difficulties in sparse data. In a word, current work cannot effectively solve the cold start problem, such as lack of user data caused by completely new users. In the part 3, I will introduce our framework. The novel deep recommendation framework we propose combines user feature extraction, matrix factorization, and neural network learning mapping. Based on the selection of specific application technology, we call this method LBD, which is LDA and BPR and DN for short. As is shown in the figure, the method is divided into 2 parts, offline learning and online recommendation. The offline part is shown in phase 1. Mashup information is used to represent the user's information in the context. The LDA model is used to process the limited service description text in the mashup data and extract the mashup description eigenvector. Then the Mashup API invocation matrix is decomposed into the potential factor matrix of Mashup and API by using BPR. After getting data support from these 2 steps, the DN was trained to learn the complex mapping of Mashup description eigenvectors and the Mashup potential factor matrices offline. The online part is as shown in the phase 2, when the new user inputs demand online, which will be processed by the same LDA model to obtain user demand eigenvector, and the potential factor matrix of user demand is mapped by DN, which has learned the complex mapping relationship. Finally, a new user API matrix is obtained for recommendation by multiplying the potential factor matrix of user demand and the potential factor matrix of API obtained by matrix decomposition in the offline phase. To effectively overcome the problem of high sparsity in datasets, we propose an LBD clustering method based on the improved LBD. The function of clustering is to divide the samples in the dataset into point subsets. According to the topic clustering method, the original data is compressed to reduce data sparsity, and the clustering results are used as a new input validation effect of the method. For sparse data, we cluster the mashup entries in the original data. In the future extraction stage, LDA can directly give the topics to which each service description belongs. In this part, I will introduce the experiment of this paper. The experiment will try to answer the following research questions. Question 1. How to tune parameters to optimize the performance of the LBD framework. Question 2. How does LBD perform in solving completely new user problems compared with the state-of-the-art methods? Question 3. How much does the performance of the LBD framework improve when the dataset becomes denser? In addition to build the corresponding mashup API matrix through the dataset, we also capture the corresponding description of mashup, 4,656 mashup classification tags, and 5 types of services. About the evaluation metrics, to measure the recommended accuracy of the method we proposed, we adopt 3 classical metrics: precision, recall rate, and F1 score. In the following comparison experiments, we use the P, R, and F1 respectively to represent them. Thirdly, about the baseline approaches. To verify the superiority of our proposed method in solving completely new user problems, we select 4 state-of-the-art methods. First, BPRKN. This method uses implicit feedback data with BPR to learn the key nearest neighbor model. Second, LDACF. This method uses LDA to analyze user text similarity and then makes recommendations based on collaborative filtering. Third, NCF. This method uses neural collaborative filtering to learn the relationship between mashups and services, then recommends relevant service. Fourth, DHSR. This method uses a novel deep learning-based hybrid approach to recommend a web service. The invocation interactions between mashups and services as well as their functionalities are seamlessly integrated into a deep neural network, which can be used to characterize the complex relations between mashups and services. Then I will introduce our experimental results and analysis in detail. In the part of parameter tuning, first, there are 2 main factors affecting the performance of the deep neural network model: the number of hidden layers and the number of neurons contained in each hidden layer. So we will try to find out the best DN structure in this experiment. The results of neural network methods with different hidden layers are shown in Table 4. The result shows that when the number of hidden layers is 2, the accuracy, recall rate, and F1 value of model are the highest. When the number of hidden layers increases to 3, the performance of the method decreases greatly. The number of neurons in each hidden layer is set to 500, 1000, and 1500 respectively, and the performance is compared in Table 5. The result shows that the accuracy decreases with the increase of the number of neurons in the hidden layer. When the number of neurons in the hidden layer is set to 1000, the method has the highest recall rate and F1 value. About parameter optimization in prediction part, we compare the selection of similar users and the number of recommended APIs. We use a control variable to optimize K and N. The results are shown in Table 6 and Table 7. So we would find out that when the number of N equals 30 and the number of K equals 15, we could get a better result of PR and F1. The dataset partitioning will affect the result of the method, so we conducted a comparative experiment of dataset partitioning on the basis of DN structure optimization. The dataset is divided into the training set and the test set according to the ratio of 8:2, 7:3, and 6:4 respectively. The experimental results are shown in Table 8. The results show that according to the ratio of training set and test machine, the recall rate R reaches the highest when the experimental dataset is divided into 7:3. When the partition ratio of training set and the test machine is 8:2, the method appears overfitting phenomenon, which is caused by the increase of the sparsity of training dataset with the increase of training set. When the partition ratio of the training set and test machine is 6:4, the method appears underfitting phenomenon, which is because the training data is small, which is not enough to support the learning task of neural network. Therefore, in this method, the dataset is divided into training set and the test set in the ratio of 7:3. In this part, we choose the K equals 15 and the N equals 30 and take the average value of the code running results of 20 times as the last result of each method. For the baseline methods, we have also carried out parameter tuning experiments to get the best performance. The comparison results of LBD and other methods are shown in the figure 4. The performance of LBD is significantly improved compared with the other 4 methods in terms of precision and recall. The precision and recall rate of LBD is 1.34 times and 1.55 times respectively of best baseline method, DHSR. BPRKN approach decompresses 0 to 1 matrix effectively and makes API's recommendation using KN method. LDACF method uses LDA model to analyze the similarity of service description text and then recommends APIs based on collaborative method. LDACF improves the performance better than the BPRKN, which proves the analysis of service description plays a key role for content-based recommendation. However, these 2 methods fail to make use of the data comprehensively. CF approach captures a non-linear relationship between mashups and services based on a neural network framework. Compared with the BPRKN and LDACF, NCF can characterize the relations between mashups and services better, thus it achieves better performance. DHSR approach adopts a hybrid deep learning-based recommendation method. Though the DHSR shows that the hybrid recommendation method has more advantages in service recommendation, our method LBD performs better than it. And we also experiment our framework on data sparsity. The experimental results for data sparsity of LBD method are shown in Table 10, and the clustering method is referred to as LBD clustering. From the comparison of the experimental results of LBD clustering and LBD, because LBD clustering carries out classification prediction based on the nature of the experimental dataset, the recommendation effect has been greatly improved, which shows that the LBD method has certain expansion in classification prediction. It is also proved that with the increase of data density, the performance of our LBD method still has a lot of room to improve. So in conclusion, in order to solve the problem of insufficiency information bring by the completely new users for recommendation, we propose a novel deep recommendation framework. At first, the deep neural network is used to extract the mapping relationship between Mashup description and the APIs offline. Then the mapping relationship between the Mashup description extracted in advance can predict matching APIs for new users through their requirements. This framework can completely rely on the text of new users' demands to recommend their services. The experimental results on real-world data sets show that the proposed LBD framework has greater improvement in terms of accuracy and recall than the state-of-the-art algorithms. Okay, that's all my report. Thanks for your listening.
Hello everyone, my name is Wang Kai. I'm from College of Computer Science and Technology, Zhejiang University of Technology. I'm very honored to be here to share my research work with you. The topic of my presentation today is combining feature selection methods with BERT, an in-depth experimental study of long text classification. My presentation will be divided into 5 parts: the motivation, related work, our methods, experiment, and conclusion. Let's start with motivation. As we all know, BERT has become one of the most effective tools for solving many natural language processing tasks, including text classification. However, due to the complexity of BERT grows quadratically with text length, BERT is not suitable for processing long text. In the actual Chinese classification task, BERT only keeps the first L tokens of the text, where L is the maximum sequence length, and BERT ignores the rest of the text. This will affect the accuracy of the classification results. Inspired by the feature selection methods, we thought that we could shorten the text through the feature selection methods. Meanwhile, we could retain most of the text information, and then we could put the text into the BERT. There are many researchers studying how to make BERT process long text, and there are probably 2 ways. The first way is to split the input text into several smaller chunks. For example, Papgray et al. Segmented the input text into several smaller chunks, and then put them into the model like BERT to obtain the representation of each chunk, and finally use either recurrent LSTM network or another transformer to perform the actual classification. Second way is to improve transformer to reduce the complexity. Dai et al. Improved the transformer and proposed the transformer XL. Transformer XL proposed a segment-level recurrence mechanism and introduced a memory module, which can keep the connection between segments. Subata et al. Improved the calculation efficiency of the transformer. They proposed an adaptive attention span that allows the model to adaptively select the context length for processing, thereby reducing the running time and memory usage of the transformer. Ray et al. Proposed the compressive transformer, a simple extension to the transformer which maps past hidden activations to a smaller set of compressed representations. Kataev et al. Proposed the reformer. They replaced the dot product attention by one that used locally sensitive hashing, changing the complexity from L squared to L log L. Bertage et al. Proposed the longformer. The attention mechanism of longformer is a drop-in replacement for the standard self-attention and combines a local windowed attention with a task-motivated global attentions. As mentioned in the title, we combine the feature selection methods with BERT. Here we use 4 traditional feature selection methods, namely TF-IDF, text rank, mutual information, and chi-squared statistic. We use MI and CHI to represent mutual information and chi-squared statistic. Considering that the key points of text may appear at the end of the text, we put forward the next two simple junction methods, tail only and head plus tail. Tail only means to keep the last L tokens of the input text, and head plus tail means to keep the first half of L tokens and the last half of L tokens. Now we will introduce our experiment. We use two datasets, namely iFlyTech and Dianxing. iFlyTech is a collection of application description text from the famous Chinese AI company iFlyTech. iFlyTech has a total of 190 categories. The training set have 12,133 texts, and the text set has 2,599 texts. Dianxing is a collection of real-world complaint texts from China Telecom. Dianxing is divided into training set and text set, a total of 580 categories. The training set has 156,834 texts, and the test set has 38,890 texts. For the experimental results, our evaluation metrics, including accuracy, precision, recall, F1 score, and Hamming loss. In order to demonstrate the effectiveness of our method in reality, we add the evaluation metric RC and AUC. Besides, we set a maximum sequence length L is 128 and L is 256. The experimental results of iFlyTech when L is 256 are shown in Table 2. In terms of accuracy, recall, and Hamming loss, the CHI plus BERT method achieves the best results. On precision, CHI plus BERT has almost the same result as BERT. On F1 score, CHI plus BERT also achieved the results second only to ExcelNet. Overall, the CHI plus BERT method outperforms BERT in 4 metrics, which means that the future selection method is helpful for BERT to process long text. The experimental results of iFlyTech when L is 128 are shown in Table 3. As can be seen from the table, the CHI plus BERT method has achieved the best results in accuracy, recall, and Hamming loss, and it is second only to ExcelNet and better than BERT in precision and F1 score. CHI plus BERT method outperforms BERT in all metrics, which proves the effectiveness of future selection. In conclusion, on the iFlyTech dataset, the CHI plus BERT method performs better than BERT, which to a certain extent shows that the combined feature selection methods help BERT to process long text. The experimental results of Dianxing when L is 256 are shown in Table 4. In terms of accuracy, the accuracy of CHI plus BERT, tail only, and ExcelNet surpass BERT, and the gap between between the CHI plus BERT and the XLNet is very small. As for precision, CHI plus BERT is the highest. Next is the TF-IDF plus BERT. In terms of recall, XLNet has greatly improved, followed by TF-IDF plus BERT. XLNet also achieved the best results in F1 score. As for Hamming loss, CHI plus BERT and XLNet both have good performance. The experimental results of Dianxing when L is 128 are shown in Table 5. It is obvious from the Table 5 that the results of most methods are better than BERT. The 5 evaluation metrics of TF-IDF plus BERT, CHI plus BERT, tail only, head plus tail, and the XLNet are all better than BERT. In terms of accuracy, the results of CHI plus BERT and the XLNet are very close, and both are 2% higher than BERT. On the 3 evaluation metrics of precision, recall, and F1 score, the TF-IDF plus BERT method achieved the best results except XLNet. As for Hamming loss, both CHI plus BERT and XLNet methods are much better than other methods. When L is 256, the ROC curve and the AUC value of each method are shown in Figure 5. We can see from the 8 pictures, for the 2 ROC curves, the results of each method are not much different, or micro AUC near to 0.96, or macro AUC near to 0.93. The macro curve of TF-IDF plus BERT is better, and the micro curve of text rank is better. When L is 128, the ROC curve of each method is shown in Figure 6. Unlike L is 256, when L is 128, the ROC curve of other methods are better than those of BERT, and the ROC curve of CHI plus BERT is the best. In conclusion, combine the 2 experiments of L is 128 and the L is 256. We can find that CHI plus BERT always has a good performance except XLNet, and the CHI plus BERT is better than BERT in almost all evaluation metrics, and is very close to XLNet in the almost intuitive accuracy. This shows that our feature selection methods are very helpful for BERT processing long text. Finally, we conclude our conclusion. We propose a method that combines the feature selection methods and the BERT to process long text. We conduct extensive experiments on public dataset and the real-world dataset from China Telecom. Finally, the experimental results show that our methods could improve the long text classification performance of BERT and achieve the effective close to XLNet on China Telecom dataset. That's all. Thank you.
Hello ladies and gentlemen, and welcome. The following presentation follows the pilot study titled A Novel Approach for Seizure Classification Using Patient-Specific Triggers. First, let me introduce myself. My name is Jamie Pordoy, and I am the lead author of this conference paper. I am a PhD scholar at the University of West London, where I research new healthcare concepts centered around deep learning, real-time processing, and the IoT edge. The following presentation will consist of 6 parts. The first part will cover an introduction to the research area and the problems that are to be addressed. This will be followed by this research methodology, experimentation, and results. Lastly, I will form a discussion and end the talk with a conclusion. I will now begin with a brief introduction to the research area. Epilepsy is a commonly occurring neurological disorder that affects an estimated 60 million people worldwide, with an incidence rate of 40 to 70 new cases for every 100,000 adults. Common symptoms manifest in the form of recurrent, unprovoked epileptic seizures, where a hypersynchronous discharge causes an alteration of one's neurological functions. Epidemiological studies indicate that up to 40% of those diagnosed will not enter long-term remission for several years, as they have become refractory to anti-epileptic treatments and have a form of drug-resistant epilepsy. Those with drug-resistant epilepsy are at an increased risk for early mortality when compared to non-epileptics, with sudden unexpected death in epilepsy, or SUDEP, documented as the preliminary cause of death. As the underlying cause of SUDEP remains unknown and without treatment, recent case studies have suggested that a seizure's onset and in turn SUDEP could be triggered by several predisposed risk and trigger factors. Although seizures are sporadic and seemingly random, studies show these trigger factors increase the likelihood of an epileptic seizure. Epilepsy trigger factors can be categorized as seizure-inducing or seizure-triggering events. Seizure-inducing triggers are caused by environmental or biological events such as light or sound and can cause a transient lowering of the seizure threshold level. Seizure-triggering events can vary based on each person's specific threshold and tolerance levels. Examples of seizure-triggering events include stress, sleep deprivation, and fatigue. A study by Furlisi and Chauvin interviewed 104 patients with epilepsy to identify the frequency of these triggers. Results show that seizure-triggering events are far more frequent than seizure-inducing, with an estimated 91% of participants listing one or more triggers as the causation of their seizure's onset. The distribution of these triggers is illustrated in this slide, with stress, sleep deprivation, and fatigue listed as the most commonly occurring trigger factors. Furthermore, we can record these predominant triggers using IoT-enabled sensors and quantitative questionnaires, which then begs the question, could they be used to assist in the detection of epileptic seizures? It is a widely held view that the most effective method of non-EEG detection is a multimodal mechanism that uses 2 or more sensors to analyze a patient's physiological signals. Multimodal mechanisms are centered around 3 predominant modalities: autonomic change, muscle tone, and muscle movement. The combination of these 3 modalities has produced promising results, with most multimodal variations attaining sensitivity scores of 70% or higher. The main limitation observed with this method of detection is the level of specificity or frequency in which false alarms are triggered. If we could use seizure triggers as an additional modality, and use a precision-based approach where machine learning models are trained using data from a single participant, then we feel that this could present a new, untested method of detection. Recent studies have tried a similar approach for hypoglycemic event detection and patient-specific classification of cardiac cycles. These studies have shown promising results by developing dedicated machine learning models that are trained using data from a single participant and then tested using unseen data from the same participant. Given the successful use of patient-specific classification in other medical fields, it is our feeling that patient-specific triggers require further investigation, as they could improve on current levels of performance and reduce the frequency of false alarms seen in current detection systems. Therefore, as we have briefly discussed epilepsy and the predominant use of patient-specific triggers, I would like to move on to this paper's research methodology. This paper presents a preliminary pilot study that investigates the potential application for using patient-specific triggers as an additional sensing modality when classifying epileptic seizures. We believe this investigation is supported by the notion that patient-specific triggers are preceding events that are responsible for initiating or precipitating a seizure. Due to the impact of the current global crisis, COVID-19, we cannot conduct a full-scale clinical trial, which in turn has reduced the size of our dataset. However, as this is a pilot study that focuses on patient-specific classification, we decided to proceed using the 2 participants we had available. Our hope is that this pilot study will be used as a preliminary component to test the validity of patient-specific triggers and enable us to calculate whether further research with a full-scale clinical trial is a feasible option. As far as we know, this is a novel concept, and there is no existing research that has used these specific triggers for patient-specific classification of epileptic seizures. The following research framework shows a high-level diagrammatic representation of this paper's methodology, which consists of 4 phases: data collection, data sampling, machine learning, and finally a comparative analysis. Based on Furlisi and Chauvin's findings, we decided to record the following patient-specific triggers: stress, sleep, fatigue, and exercise. For this study, we collected data from 2 participants with epilepsy, 1 female in her late 20s and 1 male in his mid-30s. Participant 1 was observed for 300 days, during which we documented 17 positive tonic-clonic seizures. We observed participant 2 for a slightly shorter duration of 248 days, of which 22 tonic-clonic seizures were recorded. We developed a bespoke Android application with pre-installed quantitative questionnaires to record daily measures of stress and fatigue. To record sleep, we used a Fitbit versus embedded accelerometer and heart rate sensor to measure the fluctuations in heart rate variability and body movement. We also used the Fitbit versus sensors to calculate the metabolic equivalence of participants, as this provided an accurate measure for the number of minutes that active movement occurred. Whilst it has not been documented as a commonly occurring trigger, we decided to record exercise, as it had a clear correlation with stress reduction, which in turn could help to prevent or reduce the frequency of epileptic seizures. Before we could train our classification models, each participant's dataset had to undergo random oversampling. Accurately classifying rare events can be problematic, as the frequency of positive occurrences can leave a dataset highly imbalanced. For this study, 548 instances were recorded, 509 negative instances when no seizure was documented, and 39 positive instances. To account for the varying disparity between positive and negative instances, we used random oversampling. This sampling technique balanced our dataset's distribution, as duplicate instances from the minority class were added to our training dataset. Once each dataset was balanced, we could begin to train our classification models using the patient-specific triggers. Classification is an instance of supervised learning where a classification model or classifier observes a set of input features and makes a prediction on unseen data that shares the same features. For this study, we are using classification models that predict binomial outcomes, such as yes or no, true or false, and positive or negative. The following 6 classification models were developed for this study: logistic regression, a multi-layer perceptron, decision tree, random forest, support vector machine, and naive Bayes. We then trained and refined each classification model using the same process to prevent any biases from occurring. Once each model was classified at optimum efficiency, we conducted a comparative analysis to evaluate overall performance and identify which model was best suited for classifying patient-specific triggers. To evaluate the performance of each classification model, we used the following 4 Bayes measures. Each Bayes measure is calculated using a combination of positive and negative instances. We use accuracy, sensitivity, specificity, and a positive predicted value. Furthermore, to account for the imbalances in our dataset and the use of oversampling, we constructed a multi-point ROC curve of probability. A ROC curve will plot each classifier's true positive rate against its false positive rate at multiple decision thresholds. This allowed us to measure the area under curve to assess how efficient each classification model was at predicting positive and negative instances. The combination of these 5 experiments presents a comprehensive overview for each classification model's performance and evaluation. The following slide illustrates the experimental results recorded for both participants. Table 1 summarizes the comparative analysis of our classification models for participant 1, with the multi-layer perceptron outperforming the remaining models with an accuracy score of 94.73%. Table 2 illustrates the classification results for participant 2, where the multi-layer perceptron once again outperformed the other models with an accuracy score of 96.87%. To further assess the use of patient-specific triggers, we created a third dataset comprised of the data recorded from participant 1 and participant 2. The idea behind this was to see if a more general classification model with a larger training set would outperform a dedicated model designed to classify individual participants. From the table, we can see that the multi-layer perceptron once again outperformed the other classification models, but it did not attain a higher degree of accuracy when compared to the individual classification models shown in Table 1 and Table 2. This section summarizes the findings and contributions made from this pilot study. Our experimental results indicate that patient-specific triggers can be used to successfully train and classify a model using a single person's data. Based on the experiments conducted, we can conclude that the multi-layer perceptron was the model best suited for this type of classification task. This presents a good starting point for future research where we can investigate different neural network architectures to see if performance can be improved past the standard multi-layer perceptron that was used. We observed participant 1 was more likely to have a seizure if they had less than 6 hours of sleep, whilst participant 2 was more affected by sleep on average, having a seizure when less than 8 hours of sleep was experienced the day prior. Stress and fatigue showed a correlation with the frequency of a participant's seizure onset, with participant 1 having a stress score of 3.5 or above in 88% of recorded cases. A lower statistic was observed for participant 2, who had a stress score of 3.5 or above in only 64% of cases. Although participant 2 was less affected by stress, a higher fatigue score was observed throughout, with 77% of the 22 seizures recorded having a fatigue score of 4 or above, when compared to participant 1, who had a fatigue score of only 3.5 or above in 48% of cases. Moving on, the concern about the findings of this study was the sample size that was used. Due to COVID-19, our sample size and participant availability was greatly affected, leaving this pilot study with only 2 participants. Therefore, we decided to do a preliminary pilot study with the available participants to test the validity of patient-specific triggers. If a larger sample size could be attained, then we could further validate the use of these triggers and their use as an additional modality in multimodal systems. So, I will now summarize the key points of this presentation. This pilot study has undertaken a preliminary investigation into whether patient-specific triggers from the same participant can be used to train and test a classification model. Our results indicate that both participants were more likely to experience a seizure if they had less than 6 to 8 hours of sleep and a stress or fatigue factor greater than 3.5. These findings show how participants are susceptible to triggers in different ways, which in turn reinforces the use of person-specific classification. Whilst current multi-sensor modalities tend to focus on the use of biometric sensors, such as the electrocardiogram, to formulate a prediction, using patient-specific triggers in conjunction with these sensing modalities could improve detection metrics and account for the varying diversity seen in different types of epilepsy. And finally, to our knowledge, this is the first pilot study that has proposed the use of patient-specific triggers for epilepsy detection, and the results presented here warrant further investigation in the form of a full-scale clinical trial. Thank you very much. If you have any questions about this research, please contact me on one of the 3 platforms. Thank you very much.
Hello everyone, my name is Yinghui Wang, a PhD student from Tianjin University in China. This work is a unified Bayesian model of community detection in attribute networks with parallel degree distribution. Here are the co-authors of this paper. Here is my outline. There are 4 parts in my reports. First, I will introduce the introduction and motivation of our paper. Complex networks are usually denoted and used to represent and analyze a variety of complex systems, such as social systems, biological systems, and ecological systems. Community detection is key to understanding the structure of complex networks, and applications are diverse. Community detection is denoted to divide the nodes of the network into different groups, where nodes within a group have more links or similar characteristics. The real-world complex networks usually demonstrate a variety of features, such as the scale-free property and node attributes, which are the key factors that should be considered in the community detection. In recent research, there are 2 lines of related work: community detection methods based on attribute networks, and the statistical network models, especially the works for modeling the heterogeneity of nodes. As node attributes have attracted extensive attention in the complex networks analysis, some approaches have been proposed to combine network topology and node attributes to improve the performance of community detection or community semantics. Besides, node attributes were considered as important factors in community detection. Some research also noticed the characteristics of the network. Most of these methods based on the statistical block model, which was a significant benchmark method to detect latent communities according to the abreast edge in complex networks. Most previous community detection methods considered only one aspect, and all the above methods ignore combining the scale-free feature and node attributes at the same time for community detection. Actually, considering the heterogeneity of degree and node attributes at the same time is worth studying in community detection, and faces the following 2 challenges. One is how to preserve the parallel degree characteristics during modeling the topology, and second is how to efficiently combine the node degree heterogeneity and node attributes to improve community detection results. In other words, jointly encode the varying degree distribution and node multiple attributes to make them complement each other. So in this paper, we propose a normal, unified, and pre-simple Bayesian-generated model to handle the above problem for community detection. Next, we introduce the unified Bayesian model of community detection in attribute networks with parallel degree distribution. As we can see, given an undirected attribute network G with n nodes and m attributes, the nodes and attributes are denoted as set V and set W. We define a unified Bayesian probabilistic generative model to handle network topology and node attributes at the same time. The model contains 3 types of parameters. The first type is obverse quantities, including the number of groups or communities K, the number of nodes N, the number of attributes M, the adjacency matrix A, and the attribute matrix X. The second type is latent contents, including group label Z, the content membership J, and the degree data variable eta. The third type is model parameters, including pi, b, eta, and theta. To model the network structure, we need the linker probability of node pairs. In classical statistical block model, the probability of node AI links to node VG is BZI-ZG. Considering the fact of power law feature in real-world networks, we define the degree variables eta I to each node Vi, and each eta I is assigned an expressional prior. In order to capture the heterogeneous, we use B instead. To jointly model network structure and node attributes, we define the parameters eta. In our model, the nodes can be divided into K network communities or K attribute clusters, which called topics in LDA. Meanwhile, attribute topics and network communities may not align. So we use eta R denotes the general topics distribution communicated R. When the community label of node Vi is obtained, that is Zi equals R. Then eta Rs is the probability that generating the topic of node Vi and Ji equals S. Thus, eta provides the transition from communities to topics and collaborates 2 parts closely. When we obtain the topic of node Vi, that is Ji equals S, we use theta S to generate the attributes. Then we use the variational EM algorithm and the mean field method to optimize our model. Calculating the observation likelihood P is usually analytical intractable because of the integral overall latent variables. So there is no closed form of joint post-prior P. So in the variational algorithm, we use a certain distribution family to approximate the real post-prior. In this part, we optimize the method parameters. We fix lambda equals 0.01 and update pi, b, theta, and eta. The implementation of the above algorithm is shown in algorithm 1. Next, I will introduce the experiments in this paper. We evaluate the performance of our model on synthetic and real networks and compared with 3 other methods. The synthetic network is a random network in Newman's model. 5 real networks we use are shown in Table 1. Texas, Council, Washington, and Wisconsin are 4 subnetworks of the WebKB network. Twitter is the largest subnetwork in Twitter data, and we use the normalized mutual information as the evaluation index. Here is the experiment result of synthetic network. The synthetic network contains 128 nodes divided into 4 disjoint communities with Z in plus Z out equals 16. We set H equals 50. Network topologies and node attributes share the same membership. Node attributes matrix and the community attribute matrix are shown in the figure 2. We adopt PLD-SBM as a baseline method. Other comparison methods are NEMBP and SCI. As shown in figure 2C, our model can fairly well exploit the node attributes information to improve the quality of community detection compared with another method. Then we set H out equals 8 and change Z out from 0 to 9 with an increment to study the ability to use network structures information. Our method also performs better than NEMBP and SCI. On the whole, information of attributes and structures can be better used in our model. Figure 3 is a visualization of community detection results, and the results obviously are better compared with another method. And here is the experiment result in real networks. We compared our model with the methods of 3 categories. The first one is models based on network structures, such as DC-SBM, PLD-SBM. The second is models based on node attributes, such as LDA. The third one is models based on both structures and attributes, such as PCLDC, NMMA, SCI, NEMBP. Results are shown in Table 2. Our model PLAC outperforms other models on Council, Washington, and Wisconsin, achieves larger NMIs than most of the models on Texan and Twitter. It is mainly because that the attributes of each community are clear in Texan, and the degree of nodes in Twitter doesn't obey the parallel distribution. Usually, the models based on structure and attributes outperform the models with only links or attributes. The results are further improved when considering the parallel degree distribution of each node in networks, such as NEMBP uses the heterogeneity of node degree to model the network structure, which is associated with DC-SBM. But its optimized equation is dependent on cluster level degrees rather than node level, rather than equals degree distribution over each node like our model. So our model performs better than NEMBP on datasets that have the parallel feature. Furthermore, we present a demonstration of a community semantic analysis based on the widely used data on community detection in attribute networks. Last FM from an online music system, which includes 1,092 users. And we set the number of communities is 38, as represented in Figure 4. We show the 2 examples of community interpretation. The first is a community of fans who may like heavy metal rock music, and the users in the second community performs a more relaxed and relaxing style of pure music. We give that based on the pre-parameters eta and theta. The last part is the conclusion. In this part, we proposed a normal Bayesian probability model to detect communities in attribute networks with parallel degree distributions and token a variational EM algorithm to optimize the objective function of the model. We presented a demonstration of community interpretation by applying our model on a specific science. It is similar to the existing methods that the number of communities needs to be given in advance, and we will focus on how to automatically determine the number of communities for this model in the future. That's all about my report. Thank you for your listening.
I'm honored and proud to have the opportunity to speak at this meeting. Today, I would like to present my paper, Mobile Edge Server Placement based on Bionic Swarm Intelligent Optimization Algorithm. My presentation will cover the following aspects: introduction, related work, system model and problem definition, optimization approach, experiments and analysis, conclusion. The first is introduction. With the continuous development of the Internet of Things and mobile communication technologies, mobile applications have become increasingly diverse and complex, and the demand for resources such as computing, storage, and the network is also increasing. So, in order to deal with the needs of users in the network, mobile edge computing appears. In order to solve the needs of low latency and hang-based works, the deployment of major edge servers will be the next key task. Selecting a suitable geographic location with a central geographic area to deploy edge servers and achieving the goal of minimizing network delay and balancing access resources are the current problems that need to be solved in edge server deployment. Taking Figure 1 as an example to illustrate the edge server placement. In Figure 1, the edge server is located next to the base station. Therefore, it's necessary to find a suitable location from multiple base stations positioned for edge server's deployment. As shown in Figure 1, an edge server can be responsible for placing multiple users' requirements forwarded by multiple base stations. The existing edge computing related research on the placement of edge server has the following problems. The first one is the research basis of most studies is that the relevant edge equipment has been assumed to be set in a central location, and then the access delay is studied, and the problem related to LED offline are not considered. The second one is there is almost no research on the mobile edge server placement model. The last one is most of the existing studies don't have real experimental data and environment. So, the main contribution of these people are listed as follows. 1. Express edge server placements as a multi-objective constructed optimization problem. 2. Use an intelligence optimization algorithm to find the best place of edge server. 3. Based on about 2,400 base stations operated by Shanghai Telecom, the experimental results show that our method outperforms other methods. 2. Related works. At present, there are many scholars carried out research on mobile edge service, but most of the existing research focuses on offloading mobile use server clients to the macro cloud or remote cloud to achieve low latency for mobile devices, and these studies assume that devices such as the microclouds have been placed in the mobile edge computing environment. There are few related studies on the deployment of mobile edge servers, but in recent years there have been some related research work on the deployment of cloudlet and edge clouds. 3. System model and problem definition. Related notation are explained in detail in Table 1. In the mobile edge computing environment, we define the edge server placement problem as an undirected graphical G. There are many mobile users, base stations, and edge servers to be deployed in this network. Where B is the center of all base stations, S is the center of edge servers that will be placed in the network N. E is the center of links between a base station and an edge server at a location in S. All base stations address can be used as the location of the edge server, and each base station must be assigned to an edge server. Each edge server is responsible for processing network requirements forwarded by all base stations in the edge server's coverage. Suppose each edge server is isomorphic, the conclusion capacity is limited and the same, so each edge server is responsible for processing mobile network user server requirements forwarded by all base stations with its coverage. In our study, there are two main problems we need to solve. One is the placement of K edge servers. The other is the allocation of N base stations. D is the edge server placement, and C is the base station allocation scheme. DC is the solution of edge server placement problem. So let WLDC be the workaround balance between edge servers in an edge server placement solution, and it can be formulated as follows. The definition indicates that the smaller the value of WLDC is, the more balanced the workload of edge server is. Let VBS be the communication delay between a base station B and the linked edge server S. Is the value of shortest path between base station B and the base station at location B in E. ADDC is defined as a average of all the communication delay between base stations and edge servers, and it can be formulated as follows. Transforming equation 1 to 5 into 6 as a multi-objective optimization problem denoted as problem 1. In order to obtain the proto-optimal solution or weakling proto-optimal solution of problem 1, we modify the multi-objective optimization problem into a single object optimization using weighting method. 4. Optimization approach. The swarm intelligence optimization algorithm is a Bionic simulation environment algorithm. Groom swarm algorithm is a typical swarm intelligence optimization algorithm. Inspired by this, we use Groom swarm algorithm to solve the edge server placement problem. This algorithm is named GSOESP. The GSOESP algorithm is mainly used to solve the problems of edge server location selection and base station allocation. The whole algorithm can be described as following. Algorithm 1. 5. Experiments and analysis. Datasets. These experiments use a real base station dataset of Shanghai Telecom, which contains many records accessed by 6,262 mobile users on 2,000 base stations. Using global map tools, we make a distribution map of Shanghai base station in Figure 2. From Table 2, we found that there is a large unbiased workland between base stations. Baseline approach. Top K. This approach considers workland mainly. Choose the K largest workland as the edge server location, and every base station is allocated to the nearest edge server. Radium. Select K edge servers address radium from any base stations. K-means only considers the communication delay and don't consider the workland below. Evaluation metric. Access delay. We use the access delay between base stations and edge server to evaluate the performance for all approaches. In our experiments, we let the average distance between the base station and edge server represent access delay. Workland balance. We use WL to evaluate the workland balances of edge servers. We then calculate the workland of each edge server I as W, and the workland can be computed as follows. Comprehensive performance. Comprehensive performance value means consider the true attribution of every distance and the standard deviation of the workland. Comparison results with the number of base stations. When the placement ratio R of the edge server is 0.1 and the number of base station N is increased from 200 to 300 to 2,400 as shown in Figure 3. The average access delay in GSO-ASP is the smallest, followed by K-means, Top K, and Radium. With the number of base stations N increased, the average access delay has shown a descending trend in GSO-ASP approach. When the number of base stations becomes longer and the number of edge servers greatly increase, the standard deviation of the workland of each edge server changes differently in these four approaches as shown in Figure 4. Considering the two contributions of the average distance and the standard deviation of the working together, we send the weight ratio of each attribute, lambda, to 0.5. We found that the comprehension performance of GSO-ESP approach outperforms others as shown in Figure 5. The number of base station N is 2,400. And the number of edge server steps from 100 to 5 is a step size of 100. As shown in Figure 6, as the number of edge server increases, the average access distance of base stations. Among the four approaches, GSO-ESP obtains the minimal average access distance, and Radium approach obtains the worst result. The standard deviation of the workland of the edge server was gradually decreased as the number of edge servers increased. The workland standard deviation of GSO-ESP is the smallest, followed by Top K, Radium, and K-means, as shown Figure 7. The computation performance parameter shows in Figure 8. GSO-ESP outperforms others. Finally, I would like to make a conclusion with this presentation. The problem of edge server's placement is considered as a multi-object optimization problem, and an optimal deployment scheme is proposed. The main approach is a combination of improved ground-swarm optimization algorithm and adaptive algorithm to comprehensively evaluate the performance of edge server client balance and the communication delay, and 4 different approaches. We have designed experiments use real Shanghai Telecom space station dataset, and the experimental results shows that the hardware performance of GSO-ESP approach is acceptable, and the GSO-ESP approach achieves the best performance compared to the other approaches. This paper assumes that edge servers are homogeneous, but they are heterogeneous in real system deployment. Moreover, the computation power of the edge server are different. Hence, our future work will focus on the heterogeneous edge server placement problem. Thank you very much for your kind attention.
Good afternoon, reviewers. My name is Feng Hong from Zhejiang University of Technology. Today, I will introduce my paper, a MOEAD-based approach to solving the staff scheduling problem. The report will be presented as following sequence. The background, related work, overview of approach, evaluation, and conclusion. First, the background. Due to the impact on increasing of efficiency of the staff, the decreasing the operating cost of enterprise, the staff scheduling problem had attracted the interest of many scholars. Actually, the staff scheduling problem can be considered how to assign the right shifts to the right staff on the right time period. This problem arises in many work environments, such as banks, hospitals, restaurants, and retail stores. Look at the problem example. Giving a group of the staff N and a scheduling horizon H. The shifts are assigned to the staff. Along with the evaluation matrix, we try to find the schedule with the best evaluation results based on the constraints. It seems very simple, but it's a really difficult job. Look at the challenges we list. The first, the number of the staffs. In dealing with this problem, we will face a lot of potential schedules, and this number is very prohibitive. For example, we have 100 staff, and each staff can be assigned to 3 shifts, and the total combination of the potential schedules will reach prohibitive numbers. Next, there are potential conflicts among the objectives we set, which means objectives may not reach the optimization at the same time. In other words, the optimal schedule may not be found. Finally, the fairness of the objectives. Real work about the fairness of objectives have been studied. The existing works usually focus on the objectives in total, while ignoring the fairness of them. For example, we have 80 staff. Morning we need 60, afternoon we need 40. We think the schedule prefers to choose the assignment 2. Hence, the fairness of the objectives is very important. Actually, a lot of works have been studied, but this work cannot deal with our problem well. Hence, we propose our algorithm can be divided into 3 phases: encoding the schedule, operating the mutation and crossover over the schedule, selecting near optimal schedules. First, phase 1, encoding the schedules. First, we need to encode the shift in the schedule because the schedule is fulfilled with staff, dates, and shifts. And for facilitating our computation of foreign operations in the next phrase, and these shifts should be encoded like this. The day shift is 1, night shift is 2, and the rest day is 0. By this way, the original schedule T has been changed like the new schedule T, like this. Next, we transform the schedule into a shift sequence because, as said before, we have a lot of constraints. We need to set the stage to test the assigned shift. Whether the assigned shift follows this constraint. Hence, we need to transform the schedule into a shift sequence. Just like this, the staff 1 and 2 and 1 on day 1 and day 2. The staff 2 has shifts on day 1 and day 2 is 2 and 0. The entire process of this section just like slice the shift fragments. Just like this, we make the in this picture we find a slide window. The length of the slide window is 2. This number 2 represented that one of the hard constraints means the maximal consecutive working days. In here, we set this number is 2, means the maximal consecutive working days is 2. And each step of this slide window is 1. We test the whole timetable. We just the whole time the schedule. We will find picture A and picture 2. We find the second shift 2 is changed to 0 because this shift 2 is broken the hard constraint, and it need to be changed. In here we substitute this shift 2 with 0, and the hard constraint is used to control the shifts of one staff, and when the slide window reaches the last shift of one staff, like this one is finally. This shift 1 is final shift of staff 1, and this slice window will just jump from the staff 2, the first shift, to slide. And in this way, when the slide window reaches the end of the timetable, end of the schedule, we will test another schedule from the first shift. And in this way, we set the constraint control to guarantee our hard constraint will not be broken. Next, the phrase 2, operating the mutation and crossover of schedules. There are 2 encode schedules, T1, 2, and 3. We generate randomly the mutation point of T1 and corresponding shift in the position of mutation point is 0. And the shift of T2 and T3 with the same position are 1 and 2, which means the shift 0 of the position can on T1 can be substituted by the shift 1 and 2. Which shift will be used to substitute with the shift 1 depends on the polynomial of our approach. The shift 0 is an input to the polynomial. The computed result is if the computed result is shift 2, then the shift 0 with the position of mutation point on T1 can be substituted by the shift 2. As for the crossover, our approach adopts the simulated binary crossover strategy to achieve it. It can be treated as exchanging some shift fragments of two schedules to generate a new schedule according to the crossover point. Note that the crossover point is a randomly generator. For example, there are two schedules T1 and T2. We randomly generate the crossover point on these two schedules. The schedule will be divided into shift sequence according to the crossover point. Such as that, we get 4 shift sequence 1, 2, 1, 2, 0, and 1. Then we slice these shift sequence which are not in the same schedule, just like this and this. Finally, we get the new new schedules. Note that this phrase need to be performed the constraint control in phrase 1 because after the operation of mutation and crossover, the original schedule will not broken the hard constraint, but after this operation, we will find sometimes the new generate schedule will broken the hard constraint. Next, phrase 3, selecting near optimal schedules, because we have 3 different evaluation matrices. By these 3 different evaluation matrices, it's hard to be compared with different schedules. Hence, we use type shift function to convert this evaluation matrix into 1. In this, we use the mapping distance to represent this. Next, by this way, we can use this single evaluation matrix to compare with different schedules. Next, the evaluation. This section can be divided into 5 parts. Data sets. All experiments are performed based on a mixture of real and synthetic data sets. The real part comes from the Hangzhou Center of China Telecom. This part is treated as the workload, and the synthetic data set is the stuff of each month during the above time period. Next, the effectiveness of solution. We use HV to evaluate the quality of solution generated by our algorithms. All the maximum values of the schedules are composed of the point A, and the area of the PF and A denotes the effectiveness. The HV is lower and the solution is better. Next, the parameter setting. The parameter setting of generates is set to 1000, and the rates of mutation and crossover are increased from 1.1 0.121 in the step of 0.1. And all the algorithms can work a best situation because each algorithm can be work as a best situation with this setting, with these parameter settings. And this value is the average value of all algorithms. Each algorithms are performed 20 times. Next, the experiment of each dataset. In this picture, in this table, we can find that our algorithms can perform better than other algorithms. Next, the experiment of each dataset. From this picture, we can find that we have different colors. These colors can be represent that the area which is better than other algorithms. We can find this color represent our algorithms. We can find from all the pictures we will find obviously our algorithms can work better than any of other algorithms. Next, the experiment on different maximum number of consecutive working days. We vary the working days number, and we will find under this situation, our algorithm can perform better than any others. And the conclusion, in this paper, we adopted the MOEAD to address the staff scheduling problems. We provide a set of feasible schedules instead of only one optimal schedule. And next, we show that the MOEAD can find Pareto fronts of high quality than other classical MOEAS for this problem. Next, finally, we perform the experiments of varying the maximum number of consecutive working days, which reflects the applicable of our approach in the real world. Thanks.
Hello everybody, my name is Krishna Bharadwaj. Today I'll be presenting the paper titled A Hybrid Collaborative Virtual Environment with Heterogeneous Representations for Architectural Planning. This work was carried out by me under the guidance of Professor Andrew Johnson at the Electronic Visualization Laboratory at University of Illinois at Chicago. As the title suggests, we have developed a collaborative virtual environment for architectural planning that is a hybrid of co-located and remote collaboration. The system consists of three different interfaces, that is a 2D interface, a 3D interface, and an immersive virtual reality interface, all interacting with a virtual environment for architectural planning. The 2D and 3D interfaces are developed as custom applications on top of SAGE-2, leveraging the affordances of SAGE-2 for co-located collaboration. SAGE-2 is a scalable resolution shared display windowing environment that supports collaboration. This allows multiple people to simultaneously interact with both of these interfaces. The VR interface has been developed for head-mounted displays using the Unity 3D game engine. The motivation for this work is threefold. First, in a collaboration consisting of multiple sites and users, a practical issue is the availability of hardware and other resources at every site. Hence, a system that is flexible in its hardware and software requirements for allowing a user to participate in the collaborative session is desirable. Second, each representation, that is 2D, 3D, and immersive VR, has its own set of affordances and limitations when it comes to interacting with data. Hence, a system that supports multiple ways of interacting with data can help the users by compensating for the limitations of one interface with the affordances of another. Third, project team sizes can have a wide range, with the teams being split into smaller groups of co-located people spread geographically. A system that can support both co-located as well as remote collaboration can facilitate more people from such teams to take part in the collaboration. Keeping these points in mind, we developed the 2D and 3D interfaces as SAGE-2 applications to leverage the multi-user interaction capabilities that SAGE-2 offers, thus enabling co-located collaboration. As shown in Figure 2, we developed a synchronization server that relays messages between all the instances of the three different interfaces and keeps them updated and in sync. Further, the pointer location of the users at the 2D interface, the camera location and orientation of the 3D interface, and the head location and orientation of the VR users are all conveyed to all the clients in real time as well. Thus, any action performed at any site is immediately replicated at all the sites. The position and orientation information of different users are used to animate their corresponding virtual representations at all the different sites. This allows users to know where within the scene each user is and what they are doing at any given point in time. We now look at all the three interfaces in action. The 2D interface has a grid layout with each grid block representing 1 foot. A menu button has been provided and it contains options to create walls, doors, windows, furniture objects, and flags. To create a wall, users can click on the wall icon from the menu. Now, a click anywhere on the grid initiates a new wall. The current mouse position becomes the ending point of the wall. A second click fixes the ending point of the wall to the location of the click. For quick creation of adjoining walls, this point is treated as the starting point for a new wall. The user can easily break this chain by using a designated key. To create a door or a window, users can click on the respective icons from the menu and a corresponding item gets attached to the user's pointer. When a user hovers the pointer on a wall, the attached door or window orients itself in line with the wall as a way of providing feedback. A single click will fix the door or window at that point on the wall. To create a piece of furniture, users can click on the respective icon in the menu and a new instance of the chosen piece of furniture gets attached to the pointer and moves with it. A click anywhere on the layout will drop the new piece of furniture at that point. Flags are special objects that can be used as points of reference within the scene. They can be used to draw different users' attention to a part of the scene. Flags are shown in the 2D interface as colored circles. The color of a flag is chosen randomly by the interface from a predefined set of colors. A flag's color is shared across all sites, thus allowing it to act as a point of reference within the scene. The 3D interface presents the users with an in-person perspective of the scene, rendered on a large display in a rectangular window, whereas the VR interface presents the same in-person perspective in a fully immersive head-mounted display. Flags are presented as tall, colored pillars within the scene in the 3D and the VR interfaces. This is to help users to see the flags despite being behind walls and other structures that might occlude part of users' view. A menu identical to that of the 2D interface is provided in the 3D as well as the VR interfaces. Both of these interfaces also have functional capabilities similar to the 2D interface, but with interaction metaphors that are more appropriate to 3D interaction. For example, unlike the 2D interface, newly created pieces of furniture do not follow the pointer and are placed in front of the camera and the VR user respectively. The VR interface allows the users to freely look around and walk within the scene as well as teleport to any point within the scene. Additionally, flags in the VR interface act as teleportation targets. This allows the VR user to easily reach a flag despite being anywhere within the scene, since the flags are tall and can be seen even from a distance. Typically, co-presence of different users is achieved by representing users as avatars. In a hybrid system like ours, different users have different levels of immersion, and affordances of different interfaces impose differences in how they interact with the scene. We created representations that reflect these differences. In the 2D interface, the VR user's representation shows a human icon wearing a VR headset from the top view. The camera of the 3D interface is shown as a straight line with bent edges indicating a window into the scene with a limited field of view. At the 3D and VR interfaces, the mouse pointers of users from the 2D interface are represented using 3D arrows in the scene, and they continuously move about within the scene following the pointed movements of users within the 2D interface. The VR user is represented as an avatar in the 3D interface with two rays attached that reflect where the VR user is pointing the controllers. The camera of the 3D interface is represented as a rectangular window in the VR interface. Whenever a user at the 3D interface has their pointer on the interface window, a ray is shown as coming out of the window, enabling others in the scene to identify where the user is pointing to. To assess the general usability of our system and to gain insights into how the differences in representations affect the group work, we conducted a user study. It was a group user study. It involved 4 participants per trial. 1 participant interacted with the 2D interface, and 1 interacted with the VR interface through an HMD, and 2 participants interacted with the 3D interface. We conducted a total of 5 trials. Each interface was situated in a different room within our lab to reflect a real remote collaboration scenario. The 2D and 3D interfaces were presented on large display screens running Sage 2 instances. The participants were seated in front of these large screen displays and interacted with these displays using laptops. In a third room, the VR interface was presented to the user on an HTC Vive. All 3 locations were connected through an audio conference, and participants could speak to each other throughout the study. The participants were given a brief practice session at the beginning of each trial. After undergoing the practice session, the participants were given a set of high-level requirements to design the office space. Each session was audio and video recorded. Also, every action of each user was logged, capturing details such as their location in the scene at the time of the action and the objects in the scene that the user interacted with in taking that action. A brief survey was administered to the participants at the end of the session to assess the usability of our system. Table 1 shows the results we obtained from the survey. While the results indicate that the participants were fairly satisfied with its usability, relatively lower scores were reported for the 3D interface on navigation and object manipulation metrics. We had also asked descriptive questions towards understanding any issues the participants might have had in interacting with the system. Some of the answers we obtained helped us understand these lower scores. On a few occasions, when the view had too many closely placed objects, the 3D interface made it difficult to accurately select objects. The navigation difficulty was also reported when the view had too many objects. This is mainly due to the object picking algorithm that we implemented at the 3D interface and has been fixed since the running of this user study. The overall results indicate that different representations of different interfaces to achieve co-presence did not impede the collaboration. In fact, we noted through the video recordings of the sessions that the users very quickly became accustomed to how other users perceived the space and how they interacted with the scene. Table 2 summarizes the interactions in each trial along with the duration of the trials. This data shows that the participants interacted quite a fair amount with the system and thus further supports the subjective scores from the Table 1. The chart in Figure 3 shows a breakdown of all the objects that were created by different participants of all the trials. As can be seen in this chart, except for one trial, the walls were mostly created by the 2D interface. Through the recordings, we observed that the users felt that wall creation was easier for the participant interacting with the 2D interface. We also noticed that soon after creating the walls, the participants at the 2D interface would proceed to place the doors and windows on these walls. This can also be noted from the breakdown shown in Figure 3. Figure 4 gives the breakdown of edits done by different participants at different locations. We note two things from this breakdown. First, in some cases, one of the participants worked almost entirely on particular parts of the space, whereas in other cases, all the participants shared the work for designing that part of the space, suggesting a flexible division of work. Second, VR participants generally did more interactions. When seen together with the 2D participants mostly creating walls, these results suggest that the task division is guided by the affordances of the different interfaces. From the video recordings of the sessions, we observed a few elements of the collaborative exchanges that happened between the participants. First, the participants concluded that certain aspects of the interfaces made it easy for performing particular roles within the collaboration. Second, the affordances of different interfaces favored particular interfaces for specific functionalities. Third, having different representations did not impede the collaboration. All these points help to reinforce our initial assumption that combining different interfaces with heterogeneous representations do not negatively affect the collaboration, but helps in making the group work more flexible. To conclude, we presented a hybrid collaborative virtual environment for designing architectural spaces that facilitates users to collaborate using different representations and asymmetric views. Results from a user study that we conducted demonstrated that our system enables users to freely collaborate despite having differences in interface affordances and scene representations. Finally, the results also bolstered our initial intuitive assumption that the limitations of one representation would be compensated by the affordances of another in carrying out the group task. And that concludes my presentation. Thank you, everybody.
Hi everyone, I'm the author of this paper, Zhongqing. The title of my paper is Deep Reinforcement Learning-Based Results Proving Both for Cloud Services. I'm going to explain from the following aspects: introduction for problem systems, background framework and algorithm, evaluation and conclusion. Introduction. Cloud computing has emerged as the most popular common computing model in today's computer industry. The elastic of cloud computing enables SaaS products to adapt to the changes in the workload of their cloud service by configuring and rerouting results. The available results are as close as possible to servant needs at time points. However, user requests are pointedly uncertain. It is not easy to determine the appropriate amount of results for cloud service during execution. On the one hand, if the number of results provided by the SaaS unnecessary amount cost. On the other hand, if the number of results provided by the SaaS product is less than the amount of user requests, the underprovided situation may result in lower revenues and missing customers. In order to deal with the above resource problem of cloud applications, dynamic results is used in this paper. We comment the concept of autonomous computing and deep reinforcement learning, and post a cloud aesthetic results satisfying. IBM has proved a control loop which contains 4 sticks, mounting elastics, planning and execution. We use a 2-level MAPE control loop to better allocate results for SaaS products. The first MAPE control loop is in charge of reading operator virtual machines from the ASIS product. The second MOEAD control loop is responsible for results sharing and coordination among cloud services. Problem statement. We considered a common 3-tier cloud environment which involves 3 layers as SaaS product and users. The user system tasks to the SaaS product for execution. The SaaS product reads a certain number of VM from the SaaS product and deploy cloud service to complete the request submitted by user. As the product most unlived results in the form of virtual machine. The number of user requests is conscious and floating. The main goal of SaaS product is to minimize the profits. In the cloud environment, as the product products M type of VMS, the price of every VM type M is V price. The SaaS product provides high type of cloud service. Every cloud service is composed of different types of VMS, and the service fee is C price. Cloud service server user requests constantly. Each user request contains the arrival time, the running time, and the deadline time. For more detailed dictation, see the paper. This section upholds a broad overview of the computing and deep reinforcement learning techniques. To achieve computing, IBM has suggested a reference model for autonomic control loops, which is called the MAPE loop, and is depicted in picture. The intelligent agent perceives this environment, those sense, and use the information to control effects, carry out changes to the model elements. In the government environment, the MAPE loop can be used to measure cloud results and automatically. The measured element represents cloud results. Monitor, collect CPU, RAM, and other related information from measured elements through sources. The analysis phase assesses the data received in the model first in accordance with the procedure knowledge. The plan stage purpose, the analysis data, and makes a certain action plan. In the allocate phase, the action requirements are related to the effect to execute on the model elements. Knowledge is used to control the shared data in the MAP key. Circle constraint. Each state adjusts the fingertition according to the indicators reported by the sensor in the connector environment. Deep reinforcement learning is an important field of machine learning. It has the represent advantages of deep learning and the decision-making advantages of reinforcement learning, providing the possibility to serve more complex, large-class decision-making context. The general framework of deep reinforcement learning is shown in picture. The agent used a deep neural network to represent the wave function, stage function or model, and the output of deep learning is the agent's action. Next, the agent want feedback reward R by promoting action A in the environment and text R as the parameter of the loss function. The loss function is determined based on the dynamic crowd boundaries which function is in the deep network are optimized after the training of the network model. In order to better rate and measure VM results, we propose a dynamic results forming framework for the SaaS product, which is shown in picture, with the support of the MAPE loop. It cloud service user predictive technology and DRL technology to rate the appropriate number of VMs from the S product. All this happens in Temporal and cloud service do not interfere with each other. When all cloud services compile the MAPE loop. Other MAPE circle will be start to adjust the results west caused by prediction error. The sets cloud results list of cloud source and user request blocking and the MAPE loop implements appropriate suggestions to share results between cloud sources. The effector creates a results pool based on the decision of the MAPE loop and transfer blocking text to results for allocation. After developing the SAS prompt with various cloud services in the dynamic results provisioning framework, the MAPE loop runs until there are no cloud services running in the SAS prompt. In this section, we will explain our latest results for cloud services in more detail. The context of two groups of control MAPE loops. The first group of MAPE includes morning pulse A, sys pulse A, plan with A, access pulse A. It adjusts the number of VMS in advanced by predictive technology and DRL to achieve hit cycling because the new machine general take between 5 and 10 minutes to be optimal. We set it loop every 5 minutes. The second group of MAPE includes monitoring phase B, assesses phase B, playing phase B, elapsed phase B. It loops every 1 minute and achieve vertical cycling by results sharing. Work and self-adapting mentioned. The post will run until the SAS prompt do not receive a new user request. In this section, we present an final evolution of the approach posed in the first section. First, we describe the simulation system and performance indicators, and then introduce and discuss the internal results. We simulate 5 sets of cloud services to work together and take 5 data segments with the simulates from the load tracking of the Google data certain to evaluate our the time interval is 5 minutes. The data segment lasts for more than 16 hours, including 200 intervals. The select workload data segments are shown in Figure 4, corresponding to cloud service 0, cloud service 1, cloud service 2, cloud service 3, cloud service 4. In addition, we assume that the general cycle is first come, first survive. There are 4 types of VMS offered by each product: small, medium, large, and extra large, and they have different types and costs. For combination, we conclude a group of experiments with our plots. The contrast plots are as follows. Contrast results plotted with the source-based plots and RL conclusion visit process. We create the following method for configuring our process with other select unitization with the results SLA, definition, load level, total cost and profit. Communication of CPU unitization of for process for different conclude slides. Composition of visit results of for process for different cloud slides. The average SLA variance of for process for different cloud slides. Compositions of CPU load of for process for different cloud slides. The average CPU load and the standard deviation of CPU load of for process for different cloud slides. The sum of two costs at 5 cloud slides for different process. The sum of profits at 5 cloud slides for different process. Based on the above results, we compare the CPU utilization results remaining SLA warrants, CPU load, total cost and profits of 4 approaches under 5 workloads. We observed that the proposed approach increased the CPU utilization by up to 3% to 34%, the profits by to not less than 9% and reduced the waste of results by up to about 22% to 86%. The SLA wants to less than 0.4%. The total cost saving about 16% to 48% compared with other processes. In this study, we post analytic results based on a combination of the autonomic computing and DRL in order to implicate the proposed approach. We present results provisionation framework that support the MAPE control loop and use a two-tier analytic results configuration. Our framework cloud adjusts the number of VMS influenced by workload, prioritization, and DRL to achieve heterogeneous ceiling and achieve vertical scaling by results saving work and safe tapping. Examine results using actual Google cluster tracking. Results showed that the proposed approach could increase the results utilization and decrease the total cost while avoiding SLA utilization in the future. In the future, we plan to consider the type of result request based on the proposed most to configure a more suitable cloud survival. In education, some emergent situations such as the sharp fluctuation of user requests and VM fingers will be considered. Thank you.
Hello everyone, my name is Domi. The title of my paper is End-to-End Cost Aggregation and Container Allocation for Complex Microservice Flows. I will explain my paper from the following four aspects: introduction, system, model, solution, and conclusion. Microservice flow containing a set of microservices with data dependency between each other is processed by multiple microservices. As shown in Figure 1, it implies that microservice MS1 child microservice can only be started after the microservice MS2 parent microservice has completed execution and transferred relevant data to MS1. Thus, a child microservice cannot execute until all its parent microservices have finished execution and satisfied the required dependencies. This paper focuses on the container allocation problem of microservice flow. Since entering the era of cloud computing, resource allocation methods in the cloud have been widely studied. More research on cloud application mainly focuses on resource allocation of virtual machines. To achieve performance-oriented load balancing or energy-oriented node integration with the development of container technology, some practical container allocation solutions, microservice management, container allocation will improve the overall performance and resource utilization of the system. This characteristic of container allocation helps to reduce energy consumption and achieve better system improvements and user satisfaction. Microservice flow is a new manifestation of application independence. This independence in microservice flow management dramatically improves the scalability, portability, renewability, and availability of applications. So leverage the cost and performance of complex microservice flow to find an optimal end-to-end container allocation solution with cost guarantee is also a challenge. An effective container resource allocation method not only satisfies the load requirements of the cluster but also ensures other cost indicators such as the reliability of the cluster. According to the definition of microservice flow, a microservice flow is modeled as a direct acyclic graph, where the set of vertices M represents microservice and E is a set of directed edges that represent data or control dependencies between the microservice. Each microservice is characterized as a tuple. MS request, resource, cost, set. Well, MS request is the number of microservice I requests required to satisfy one application workload. Resource I represents that computational resource consumed to satisfy one request of the microservice I. Cos I represents the cost parameters of an instance of the microservice I. Set I is the set of consumer microservice for the microservice I. Since the motivation for this work is to use the composition of microservices in the workflow domain, the composition patterns are based on structure elements are used in workflow descriptions. Service in a microservice flow can be composed based on 4 basic modes: sequential mode, loop mode, conditional mode, and parallel mode, as shown in Figure 2. A complete microservice flow can be easily decomposed into these 4 modes. Applying this procedure, the aggregation can be performed on the basis of each composition pattern. It has presented a composition model that can serve as a basis of aggregation of service properties regarding cost dimension. Inspired by it, this paper used cost aggregation to model the cost of the entire microservice flow. There are 5 aggregation operations for developing an aggregation formula, including summation, average, multiplication, mean, and mass. Here we choose cost I as response time, reliability, availability. These 3 indicators are the most representative of cost. Based on them, the aggregation method of microservice flow is given. Table 1 presents the response time, reliability, and the availability calculation formulas. Based on the 4 basic relations of sequential, parallel, conditional, and loop, respectively. Container allocation mechanisms of microservice flow are based not only on the resource capacity but also consider the nature of the workload. Each microservice of the microservice flow has multiple run instances, and each microservice instance is encapsulated in one container. The scalability of microservice flow means that the container allocation can be appropriately scaled according to the resource usage rate, ensuring that some microservice instances wouldn't become the performance bottleneck of system. The first optimization objective is the communication cost. Communication cost among microservices is related to key factors. The network distance between containers assigned to interoperable microservices and the number of requests between the 2 microservices. Consider that consumer microservice and provider microservice may run multiple container instances simultaneously. This paper used the average network distance of all the container pairs between consumer microservice and provider microservice to calculate the communication cost between 2 microservices. For the second optimization objectives, we consider that the cluster needs to be load balanced. The cluster is balanced when the use of the loads is uniform across the cluster. The consumption of computational resource is uniformly distributed among the virtual machines. A high scale of a microservice is penalized when the container is underused, and a low scale is penalized when the number of microservice requests is very high. With scale changes, we can achieve automatic elastic management. We use the standard deviation of computing resource usage to evaluate the balance of the cluster. The resource consumed by each node are uniformed in this formula. The container allocation problem is represented as a multi-objective optimization problem along dominated certain genetic algorithm tool, which is considered a standard approach for multiple objective optimization problem in resource management problem for container allocation. An SC-GAT tool has high computational efficiency and high-quality solution set when processing the low-dimensional multi-objective optimization problem. In order to further improve the diversity of the population and prevent the algorithm from converging to a local optimal, we propose a heuristic of an SC-GAT algorithm in this paper. The algorithm introduces opposition-based learning in the iterative process of the population, and a crossover and a mutation strategy of DE algorithm is applied to an operator. We use the basic steps of the SC-GAT algorithm, then the DE algorithm and opposition-based learning are used in the new individual generation stage to strengthen the population diversity and accelerate the algorithm convergence. In differential evolution algorithm, the most normal feature is its mutation operation. In the initial stage of the algorithm iteration, the individual difference of the population are considerable. Such a mutation operation will make the algorithm have robust global searchability. By the end of the iteration, the population tends to converge, and the difference between individuals decreases, which makes the algorithm have strong local search capabilities. Opposition-based learning applies the opposition-based learning to the iterative process of the population, calculates the reverse individual for the individual X in each generation of the evolution process. The comparisons for the three algorithms are performed in two aspects: communication cost and load balancing of containers. Among them, we need to normalize to optimization objectives. As shown in Figure 3, experiments with 10 workloads and 100 loads are performed. We can observe the change of the iterative process of two optimization objectives under constraints. A is an iterative process of communication cost for the three algorithms. We clearly see that the communication cost decrease as iteration process. This also means that the distribution of load is ideal. Figure 3b shows the iterative process of the standard deviation. We can see that the standard deviation value gradually decreases with the process of iteration, which also means that the load between the containers is approaching equilibrium. In this paper, we define an end-to-end cost aggregation model for the complex microservice flow and formulate the end-to-end container allocation problem of microservice flow as a nonlinear optimization problem and propose an ONSGA2D algorithm to solve this problem.
Hello everyone, my name is Jie Xiaogan. I'm currently pursuing the master's degree at the Shanghai University. I'm really glad to attend this virtual conference to make a presentation. The paper I will present today is a DQN-based approach for online service placement in mobile edge computing. It mainly talk about how to improve the quality of service and minimize the total latency of arrived tasks in a long term in mobile edge computing. First, I will introduce the background of this paper. With the proliferation of mobile smart devices, many new computation and data-intensive applications with low latency requirements have come forth to mobile devices. Unfortunately, traditional cloud computing cannot meet the requirements of the applications. Due to the long data transmission time, to address the issue, mobile edge computing is put forward to provide services to other applications by deploying computing resources at the edge of Internet. By serving computation tasks on the edge, the demands of novel applications can be satisfied. These base stations equipped with high-performance computing service which can provide computation resources to mobile users. However, due to the stochastic demands and different computing resource required of each service, as well as the limited resource and the dynamic network conditions of the base station, when numerous computation-intensive tasks arrive to the base station in real time, the base station faces how to solve the problem of service placement. The base station shall determine which service to be placed on the 5G-enabled base station. Next, I will introduce the related works about the problem. Most of these works considering stationary involvement in mobile edge computing networks or assume the future dynamics like user mobility can be predicted in advance. We consider switching latency incurred by service migration and the waiting time spent by tasks for processing at the edge in a 5G-enabled network and provide a deep reinforcement learning-based approach to deal with the unknown future information. Next, the models of this paper will be introduced. As shown in this figure, numerous tasks arrive to the base station in real time, and the cloud has all services and adequate computing resource to execute the tasks of a certain type or on an edge server. The corresponding service should be placed firstly. We consider a library of allow service and are provided by the mobile edge computing system. We assume different services have various amounts of associated data and require different CPU frequencies to process tasks. Each edge server can migrate one or more services from the cloud to his locality in an online manner. However, which services can be placed in is restricted by the limited storage space and the computing ability of an edge server. In each time slot, we assume that the arrival of tasks served by service allow follows a presumed process at some rate. Besides, we assume the required CPU cycles of each task served by service allow follows an exploitation distribution. According to the real-time arrives tasks and the computation requirements, the base station needs to make the service placement decision online. In other words, the base station should determine which service to be placed on the edge in the current time slot. We employ a binary variable to indicate whether service allow is determined to be placed on the edge server or not in time slot T. Next, let's discuss the switching latency, the serving latency, and the offloading latency incurred by different service placement decisions, which are described in details as follows. As for switching latency, to migrate a particular service from the remote cloud to the edge server, a certain amount of time is spent for transmitting its associated data, which is referred as switching latency in our work, which depends on the data size and the service allow and the network condition between the base station and the cloud in time slot T. according to the service placement decision in the last time slot. We can derive the overall switching latency incurred by a current service placement decision as this. About serving latency, note that only tasks served by the service placed on the edge server can be processed on the base station, while the other tasks have to be offloaded to the remote cloud for execution. We first analyze the latency incurred for completing a task on the edge server, which is referred as the serving latency. Serving latency including the wait time and the computing time. We employ a specific MM1 queue to model the execution process of a task served by service alone on the edge server. As for offloading latency, we consider the cloud has all services and adequate computing resource, and the executing time of a task offloaded to the cloud can be ignored. For a task whose required service alone is not placed on the edge server, we assume the expected time spent for transmitting its input data to the cloud is 5. It depends on the input data size and the network condition between the base station and the cloud in time slot T. Therefore, the overall offloading latency incurred by a service placement decision in time slot T can be obtained as this. Followed by, I will present the problem formulation of this paper. In this work, we aim to find an optimal service placement policy for the base station and the objective to minimize total completion latency of all tasks over time. Without complete future information, it is difficult to obtain the optimal service placement strategy. To this end, we propose an online learning-based approach for the problem via adopting reinforcement learning, which is applicable for decision-making in stochastic and dynamic environment without any future information in play. Where we adopt a Markov decision process model to describe the process of online service placement decisions made by the base station. Each state represents the information observed from the mobile edge computing system in time slot T. Especially, state ST contains the service placement in time slot, the arrivals of tasks in the current time slot, and the current network condition. About action in each time slot T, the base station needs to make a service placement decision according to the current state, determine which service placed on the edge server. After taking an action, the base station will receive a reward from the environment. We define it as a compound reward function with considering both three objectives. Here, the service placement control policy can be seen as a mapping from the state to action. Then we reformulate the online service placement problem into determining an optimal control policy to maximize the long-term discounted cumulative reward obtained. Then, the approach proposed in our work will be introduced. Here, we propose a DQN-based approach for the policy determination problem, as shown in this figure, which consists of two phases, that is, action generation and network training. In the action generation phase, the base station observes the current state ST, input the state to the online network to estimate the value of each action under the current state. At last, the optional graded strategy policy is applied to choose the action to be taken. It means after taking action, the next state and the reward are given by the environment. The process of this interaction between the base station and the environment is recorded as an experience stored in an experience pool. In the network training phase, we employ the experience replay technique and attacking network, which has the same structure with online network but different parameters to train the parameters of the online network. The details of network training are described in next page. Now we introduce the details of network training. In each training phase, where a batch of experiments are forcibly randomly sampled from the experience pool, denoted by J. For each sampled experiment in J, we first input current state into the online network to obtain the estimated action value. Then input next state into the online network. We obtain the next action with the maximum value. Next, we obtain the target action value through this equation. Finally, the parameters of the online network can be updated by this. Next, some simulation results are shown to evaluate the performance of our approach. We conduct extensive simulations to evaluate the performance achieved by our proposed approach, compared with 4 baselines. Listed as follows: cloud processing only approach. All tasks are offloaded to the remote cloud directly. Stochastic approach. Each service is randomly determined to be placed on the edge servers or not. Service priority approach. As many as possible services are placed on the edge server under the storage space and the CPU frequency limitation. Task priority approach. Services are placed on the edge server one by one. The service which can serve more tasks in the current time slot is selected each time. The metric is the total reward over time achieved by each approach. Given the limited time, we won't go into details to introduce parameter settings. We firstly study the effect of different parameters on the convergence performance of our approach. We plot the total reward that could be received by the base station at each episode when the batch size and the update frequency of target network. We can find that our approach can be converged no matter how the parameters changes. However, different parameter settings of our approach have different convergence performance. Thus, according to the evaluation results, we set batch size to 64 and set the update frequency as 40. The parameters of the target network are updated once when the parameters of the network have been updated 40 times. Next, we evaluate the performance of our proposed approach compared with the 4 baselines on the different parameter settings. As shown in figure, we plot the rewards and achieved by different approach when the number of time slots varies from 50 to 250. We can find that the cloud processing only approach achieves the worst performance due to the long data transmission delay to the cloud. Furthermore, it can be found that the task priority approach achieves better performance than the other baselines, as more tasks can be served by the edge server. However, it obtains the large total latency than our approach due to the increase of the switching latency introduced by frequent service migration. It is obviously our approach achieves best performance on the different settings of the number of time slots. Next figure presents the rewards achieved by the 5 approaches when the number of services belong to 2, 4, 6. When there are only 2 services, the performance of our approach is the same as the service priority approach and the task priority approach, because the 2 services can be placed on the edge server at the same time. With the increase of the number of services, our approach outperforms to other baselines, which indicates our approach is suitable to complex service placement scenarios. Finally, I conclude our work. This work focused on the online service placement problem in a 5G-enabled mobile edge computing system. To solve the problem, we propose an approach based on deep reinforcement learning to obtain the optimal service placement policy for the base station. Extensive simulations are conducted to show that our approach achieves better performance compared with the baseline approaches. Okay, that's all. Thanks for you watching and listening.
Hello, my name is Hamza Slak. I'm a postdoc and a member of the Human-Centric Security team within CSI Rose Data 61 DSS Group, Melbourne, Australia. It's my pleasure to share with you this research work that we have been working on recently. Myself, Mohan Barwal-Shhetri, and Marty Hrubler, towards a trusted collaborative medical decision-making platform is the title of the paper that I'm going to present today. Let me start with a bit of context. Medical decision-making has become more challenging in recent years, mainly due to the increased number of available treatments, diagnoses, and therapeutic options. For this, patient participation is vital for medical decisions. Informed consent and shared decision-making are two important processes that promote patient participation and autonomy in such situations. On the one hand, informed consent is a legal process that refers to an individual's explicit authorization of a medical intervention, especially in treatments involving high risks. On the other hand, shared decision-making is an ethical approach that seeks to enhance patient choice by incorporating their preferences into the healthcare decisions, particularly when multiple comparable medical choices exist. In other words, it is a way to ensure that the patient's voice is heard as choices are made. And as you can see in this figure, shared decision-making is the key component in what is known today as patient-centered healthcare. Traditionally, shared decision-making has been considered as a one-off dyadic encounter between a patient and his or her physician within the confines of a consultation room. Yet, in practice, there are several other stakeholders involved, and the decisions are influenced by different determinants, including social, cultural, financial, and legal ones. For example, family circumstances, relationships, self-esteem aspects, etc. And decisions are naturally supposed to be shaped over time as opposite to single, discrete encounters. So in this paper, we included two illustrative real-life scenarios, and I will focus on one of them to motivate the rest of this presentation. Let's consider an early-stage breast cancer patient who has to choose between two treatment options, mastectomy and lumpectomy with radiation. Based on clinical evidence, both treatment options produce high cure rates. So the patient can collaborate with a number of stakeholders, including but not limited to her physician, surgeon, radiation oncologist, medical oncologist, and family members to select the best option that meets her emotional and situational needs. Enabling consensual and collectively accepted decisions is paramount to ensure that the patient gets the best possible medical option that considers her personal preferences while also balancing the healthcare provider's recommendations and family members' wishes. However, there are many challenges that need to be taken into consideration. Firstly, in real life it is not always possible to reach consensus in a single clinical encounter. Second, the patient and other stakeholders may not want to reveal their preferences over the treatment options or any other health or personal sensitive information for a number of different reasons. Moreover, a couple of questions need to be considered. Who takes responsibility if the selected treatment option does not yield the desired outcome, or worse still, results in an adverse outcome? And how to know which decision in the clinical encounter is the cause of the adverse outcome? Finding answers to such questions requires having documented evidence about the sequence of decisions taken over the entire clinical encounter. And the use of clinical diagnostic notes, traditionally stored on paper-based mediums, is no longer acceptable, as we now live in the era of digital health. As an example, electronic health records are now the recommended standard to exchange data between healthcare providers. So bottom line here is paper-based records and face-to-face consultations are now considered outdated and less effective and no longer expected to meet patients' high expectations of getting the best possible healthcare options. So, for these reasons, we posit that there is a need for a practical digital platform that enables collaborative medical decision making instead of shared decision making. Collaborative medical decision making occurs whenever two or more individuals contribute their diverse knowledge and expertise, but also personal preferences to the decision making process. And this is exactly what the patient needs. Second, the platform should provide mechanisms for iterative consensus building instead of the traditional single round discussion between the patient and his or her physician, which leads us to the necessity of supporting multiple stakeholders' participation, not just the patient and the doctor. Another important factor that needs to be considered is the privacy, confidentiality, and security of sensitive personal and health data, including preferences and decisions. In addition, the platform needs to enhance trust among the stakeholders throughout transparent communication, but also permitting decisional authority to lie with one or more of them, especially the patient. Last but not least, maintains provenance, accountability, and traceability. If all of these elements are provided, then the collaborative medical decision-making process can effectively help the patient decide the best possible healthcare option. To the best of the author's knowledge, none of the existing collaborative medical decision-making solutions address all of these challenges. What we proposed in our paper is a novel conceptual framework and reference architecture for a trusted collaborative medical decision-making platform that addresses some of those challenges. Prior to defining the different platforms component that you see on this figure, we started with the ecosystem. We identified all potential contributors to the collaborative medical decision making and their explicit roles, from the patient, core medical team, non-core medical team, family members, hospital representative, insurance agent, fellow patients, to clinical evidence base and unregulated information sources. Then, considering all of these contributors, we defined the top requirements that the collaborative medical decision-making platform should satisfy. Based on those requirements, we proposed the architecture with three components to cover them. In particular, we proposed the integration of a consensus building mechanism with blockchain technology to ensure trusted, secure, privacy-preserving, and confidentiality-preserving interactions leading to the final decision. The platform can be built on top of a private or permissioned blockchain owned by a trusted consortium of hospitals, insurance companies, and medical research institutions. So the first key component is the identity manager, which provides interfaces for registration of the participants in the collaborative medical decision-making process. It also provides authorization to those participants to access various functions on the blockchain, such as which party has access to which transactions. Second key component is the consensus builder, which is responsible for managing the entire collaborative medical decision-making life cycle, including iterative decision-making, selection, and contracting. It uses an appropriate consensus building mechanism to generate a decision that is consensual and collectively accepted. The third and last key component is the transaction ledger. The transaction ledger is responsible for recording the provenance of the collaborative medical decision-making process. Every interaction between the consensus builder, the patient, and all other contributors are recorded in the blockchain using a time-stamped workflow. This includes the interim decisions as well as the final group decision that is acceptable to the patient. This ensures auditability and enables evidence for legal remedies in the case of negligence or an undesirable outcome resulting from the medical intervention. In the paper, we also included a diagram to demonstrate interactions between the different components of the platform. We considered the breast cancer patient scenario to illustrate how the proposed platform could be used in practice. So the idea again is that the patient goes through the collaborative medical decision-making process to decide the best possible treatment option. The key contributors in this scenario are the patient, principal clinician, multidisciplinary cancer team, fellow patients, and the insurance company. So we demonstrated how both consensus builder and transaction ledger components interact to ensure that the collaborative medical decision making is iterative, trusted, secure, privacy preserving, confidentiality preserving, and auditable, while supporting the group to reach agreement and provide a ranked list of treatment options, which is then presented to the patient to help her make the final decision. Well, this is pretty much everything we wanted to share with you today, and I guess it's time to wrap up. So in the paper, we presented our vision for a trusted collaborative medical decision-making platform that shifts medical decision-making from the confines of a consultation room and into a distributed digital environment in which the stakeholders are able to freely express their preferences over the available medical interventions. We identified the main requirements for realizing such practical platform, including distributed data and decision sharing, as well as data and decision provenance. Then, based on the requirements, we proposed a conceptual framework and reference architecture that combines consensus building with blockchain technology. As future work, we will try and explore some of the human factors that might encourage or deter the uptake of digital health services such as our proposed platform. This is a work in progress, and we are still working on a first prototype for the platform. This is it, and thank you for your attention.
Hello everyone. Today I will introduce to you the work of our team, code prediction based on graph embedding model. In our coding or reading code process, we may find that some code are missing. As shown in this code, there is a missing position. Prediction node is the location of the missing node. Nowadays, a lot of code are generated every day. How to use the extending source code to prediction missing node has attracted more and more people's attention. This question is our research content. In extending research, people think that code is also natural language. So, natural language processing method can be used to solve this problem. The probabilistic model, NGRAM, and deep learning were originally used in this field of NLP. But when we applied it to this problem, the prediction accuracy is low or the interpretability is poor. In continuous research, people find that the tree data structure of AST, which transformed by the source code, as shown in this picture, is transformed by the source code. We found it contains a large number of structure features. If we can extract the effective structure features, the prediction accuracy may be improved. So we use the AST to help us extract the future data. As shown in this picture, it is a piece of the source code AST, where the leaf nodes corresponding to the code nodes in the source code, and only the leaf nodes contain two attributes of type and value. So we extract the AST up path and down path. The node's up path contains hierarchical structure information, and the down path contains the local information of the node. The node path consisted of up and down paths. Therefore, it is obviously that paths of different lengths contain different information. But it is noted that the longer path, the higher the accuracy. The parent node of the prediction node is the important information we already have. For example, if we predicted the leaf node logging, we need predict the type first, name node. So the name node, the parent node, is attributed node. After we predict the type, the name node is the parent node for logging. We can use the parent node attribute to help us to solve this problem. Is the key point. Next, it is a problem definition. Training graph G is a graph converted from the AST's node path of the source code field. Source code field converted to AST. Then we extract the path of the node. Those paths are transformed into a graph, and we use the node to vector algorithm to extract the node sequence. and embedded it as a node vector. The predicted value is determined by the calculating the vector similarity between the candidate value and the parent node of the predicted node. The similarity calculation function is a cosine function, which can effectively calculate the prediction node. The type or value with the greatest similarity is used as a prediction value. So this prediction problem is transformed into a mathematical problem. The TV as the type and value is the combination of the prediction value of the missing node. And next, we introduce the architecture of this paper, which is mining divided into 3 parts: data processing, node-to-vector algorithm, and similarity calculation. We extract the structure paths in the source code and convert those paths into a graph, and use the node-to-vector to convert the path into a vector of fixed dimension. Then we calculate the similarity between the candidate value and the parent node to obtain the prediction value. We will introduce this part in detail. Okay, first we introduce the data process. After we extract the AST from the source code, we can use the parent node of the prediction path to flatten the all paths. We divided the paths containing the same parent node into a set and transformed them into a graph, as shown in this picture. The parent node of the predicted path is name node, and all relevant paths saved in set I. Those paths parent node is name node. Then we convert the set I to a node graph. The advantage of this process is that the parent node is used to filter out the most relevant paths to the prediction node, and the redundant node paths are removed. It is not only accelerates the calculator process, but also improves the accuracy of the prediction. The next is node-to-vector. Node-to-vector is an algorithm that extracts the sequence of the graph nodes and embeds them into a fixed dimension vector. The method of the node sequence extraction is shown in this figure. The probability P of the next node of the V is related to the weight of the edge WVX and alpha PQ. The WVX is related to the number time of the node appear in the path or in the source code. The parent P can control the probability of the return to the node T, and the parent Q reflects whether the node sequence is extracted by the deepest first search or the breadest first search. During the experiment, we found that the effective DFS DFS is better. That is P larger than 1 and q less than 1. If p equal to q equal to 1, node to vector algorithm is the same as the prototype deep work algorithm, and the next node is random select. So we can obtain the node sequence of the related feature by adjusting the range of the parameter p, q, and the weight of the related path. In the experiment part, we extract 10,000 training field and 500 test field in the GitHub. We traverse all the data set and find that there are 132 categories of the type, which is determined by the program semantics. There are 50,000 categories of the value, which are determined by the programmer. The prediction result of the model is improved compared with the experimental result of baseline, which used LSTM and the pointer mixture network. Our experiment is below. WP indicated that the weight is added and the parameters are adjusted in this model. NW and NP means that no weight and adjustment parameters are added in the model. We can see our experiment result is better than baseline. The influence of the path length on prediction accuracy is shown in this table. It is noted that the longer the path, the higher the prediction accuracy. Too long a path will increase the repetition between the paths, resulting in reduced prediction accuracy. Among them, the difficulty of the prediction value is greater than type, because of a large number of the candidates of value, and the many values are determined by the program themselves, which are difficult to predict. And during the experiment, we found that there is a code structure in AST. And shown in this figure below, there are some fixed code structure for package import. But there are the following three structures. We can see this picture. Code structure here. By searching the source code field, we can effectively filter out irrelevant candidate value. The reduction of the candidate table can improve the prediction accuracy and accelerate the experiment. And in the future worker, we will use the code structure to further extract the structure pair and extract the semantic structure features. And we also use the gated graph neural network. The gated graph neural network has a stronger ability to process graph data, and the accuracy in the model may be further improved. So that's all. Thank you.
Hello everyone, I'm very honored to give this presentation. I'm Fang Rong from Zhejiang Normal University. The title of my presentation is Differential Prevent Location Preservation with Staircase Mechanism under Temporal Correlation. I'm going to give this talk in 4 parts. The first part is in the introduction, including the background, purpose, meaning, and practical application. The second part concerns the proposed outline dedicating algorithm. The third part is related to experiments, and then the last part summarizes the main conclusions. LBS is a kind of basic service in collaboration applications. With the development of posting technologies and the popularity of mobile internet and smartphones, location-based applications have implemented into our daily life, such as location-based points of interest searching, location-based games, location-based commons, and location-based social networks. To enable the location-based applications, users have to share their location to service provider. However, the disclosure of users' location could raise serious privacy concerns. In order to protect the location privacy of users in LBS, various location privacy preservation technologies have been proposed. These technologies can be classified into 3 categories, such as cryptographic, autonomic-based statistical privacy, while PIR and MPC are based on cryptographic. However, they tend to be computationally expensive. Anonymous location protection methods such as k-anonymity or ad hoc uncertainty models and could not provide rigorous privacy. Differentially privacy has been widely recognized as a leading privacy preservation method in both industrial and academic community, as it provides a formal and provable privacy guarantee, and it can preserve privacy against attackers with arbitrary background knowledge. Traditional location preservation methods only consider statistics senior or perturb the location at a single time space, without considering the temporal correlations of a moving user, and hence are valuable to various inference attackers. Therefore, we propose a new presentation mechanism, such as staircase mechanism based on data location set. Figure 1 is location realist framework. A mobile device, such as mobile phone, need to send the location information to a server. It sends the real location directly. The user's location privacy will disclosed. Therefore, it is necessary to send the real location to the noisy mechanism firstly, then send the noisy location to the LBS server. In order to protect users' location privacy under continued time space, we propose a location preservation framework. If we want to release a location of a time steps, we should contrast a data location set for it, and then we adopt a differential privacy mechanism to release a perturbed location. Step 1. Grade partition. Partition the map area with grade where the dataset is located. Step 2. Calculate the transmission metric M between locations. Step 3 calculates the period probability vector under each time steps, where the period probability refers to probabilities before releasing the perturbed location. Then the period probability vector at time step t is calculated as follows. Step 4 calculates the post-probability vector under time steps as follows. To make it easier to understand, Table 2 shows the follow of alternate calculation of period probability vector and posterior probability vector. The posterior probability vector can be obtained according to the emission probability and the period probability at time step t. Allocation 1 is the implementation process of the proposed framework. Step 1, 2, 3 calculates the period probability vector at time step t. Step 4 to 10 is the location releasing process. Specifically, when the user's location needs to be released at time step t, delta location is contrasted and the real location is hidden in the delta location set. If the real location is not in delta location set, we choose a surrogate location in delta location set. Then we generate the perturbed location through adding noise to the real location or the surrounding location. Finally, we release the perturbed locations. Step 11 calculates the posterior probability vector, which is subsequently used to compute the period probability for the next time step t81. When the location at time step t and t81 need to be realized, we repeat the above process. The process of generating delta location set and the process of noisy generation are shown in details in Allocation 2 and Allocation 3, respectively. In this section, we evaluate the performance of proposed SM-based location perturbation allogram on geo-live date. We compare it with LM and PIM in terms of the size of delta x, draft ratio, and distance, the pressure and recall on KNN query. Figure 2a shows the original trajectory. Figure 2b, 2c, and 2d shows the realized location under each time step, which we can see that the realized locations of SM are close to real locations compared with LM and PIM. It means that SM has less presentation at each time steps with epsilon equal 1 and delta equal 0.01 compared with LM and PIM. Figure 3 and Figure 4. Figure 5 shows the change of size of delta x over time, the change of draft ratio over time, and the change of distance over time. Respectively, when epsilon is equal 1 and delta is equal 0.01. Figure 3 as a whole, the difference between size of delta x is than 0. The the size of delta x generated by SM is less than that generated by LM and PIM. It shows that SM achieves the same privacy budget with less noise addition, and we get higher data utility in most cases. Figure 4. Orange line is close to 0. It means that SM has a smaller drift ratio than LM and PIM. Figure 5 shows the SM's distance is less than LM's and PIM's distance. Figure 6 is impact of epsilon and delta size of delta location set. It shows that the size of delta location set generated by SM is smaller than LM and PIM under the same delta. It shows that SM provides high data utility than LM and PIM in most cases. Figure 7 is the impact of epsilon and delta on drift ratio. Figure 7a shows that the drift ratio of SM is smaller than LM and PIM under the same epsilon. It shows that SM provides higher data utility than LM and PIM. Figure 7b shows that the drift ratio of SM is smaller than LM and PIM under the same epsilon. It shows that SM provides the higher data utility than LM and PIM in most cases. Figure 8 is impact of epsilon and delta on distance. It shows that SM has a smaller distance and better data utility than LM and PIM, and it shows that SM provides higher data utility than LM and PIM in most cases. In order to verify the utility of realized locations, we use the KNN query on 100 trajectories, which has 500 time steps, to obtain the query precision and recall under each time step. We use KNN on the original trajectories and KNN on the realist trajectories. When epsilon equal 1 and delta equal 0.01. Figure 9 shows the SM provides more accurate query results in most cases. A differential privacy location preservation method based on staircase mechanism is proposed to solve the problem of location privacy preservation under temporal correlations. Consider the temporal correlation between locations. This method protects the provenance of the user's real location in each time steps, make it difficult for the advisor to infer the user's real location from the realized location information. Experiments show that SM has a good utility while achieving the effect of location differential privacy. However, this method does not take into account the privacy preservation level of the user's location, and the default location posted by the users is a strong sensitive location. The further work will consider the proposed privacy level allocation of users' location, and a more privacy budget should be allocated to the higher sensitivity location so that it can be fully protect. For weakly sensitive locations, this provisioning budget is allocated to improve the available location data on the premise of certifying differential privacy preservation. My presentation is over. Thank you all very much for taking the time to listen to the presentation.
Hello everyone, my name is Lei Yuxiao. Today, the subject of this report is Technical Implementation Framework of AI Governance Policies for Cross-modal Privacy Protection. It is related to the privacy resource protection in virtual community. At first, let's introduce some background knowledge of this report. First of all, we need to make it clear that the purpose of this research is to establish a privacy resource protection framework for AI governance. What is privacy resource? In the past, you may say it is telephone, address, or income of someone. But in the virtual communities, privacy resource means the virtual chance and the user-generated contents. The virtual chance is the digital chance left by the user in the virtual community, such as the record of the user browsing the web. He may click a button or stay on a page for a long time. The UGC is the content posted by user in virtual community. It has many forms, such as image, text, or video, and it can include everything that user wants to express. The privacy resource can be classified into three types: data, information, and knowledge, according to their own attribution. Such as, this is a data, we just know it is related to a special user, but we don't know what the relationship is. This is the information. It can express the relationship between users and others. For that, we know the user A is a patient suffering from the AIDS, but not an AIDS doctor. This is knowledge. It is a prediction of user behavior based on information. For example, AIDS patients may need drug B to sustain their life. The privacy resource can be transferred to generated new privacy resource, like this figure. There are three kinds of transition methods, including the first-order transition, multi-order transition, and the technical transition. The first-order transition means the one input but multiple outputs. For example, we can deduce the hometown, age, or birthday of someone from its ID number. The multi-order transition means the multi-input but one output. For example, the average grade of the class can be calculated according to the grades of all members of this class. Both of the above two methods is based on the common sense reasoning. The technical transition is completed by the assistance of technology and other resource contents. It is difficult and not everyone can complete. For example, someone can infer when and where the phone was taken from the elements in a phone, while others can't. After transition completed, all of the privacy resource compose a DIKW graph of user. The graph allows the visit to assist and will output the corresponding privacy resource according to the visit's purpose. In the part 2, we start with the calculation of privacy resource to establish a framework for AI governance. At first, the virtual community extracts privacy resource from virtual chains and UGC of user and storage them in the DIKW graph that can be accessed by others. For a visit, send a visit request to the virtual community. The virtual community will transfer privacy resource to visit according to their access requirements. When the risk of privacy resource leakage is less than the safety factor, at last, the visit will exploit and develop privacy resource obtained from virtual community to achieve their own purpose. In the calculation of privacy resource, the AI system needs to protect the value of privacy resource. The first is fairness to everyone. The number 2 is personal security. Number 3 is financial security. Number 4 is peace and quick. It means the user maintains a virtual image that is different from the real image in the real world, and he wants to maintain this stance without being disturbed by others. The number 5 is autonomy, which means the individuals can act and choose or do what they want to do fairly. Number 6 is integrity against commodification. The commodification refers to the behavior puts money above everything, including the personal life or human natures. It is the behaviors we must to oppose. The last one is the reputation. It is closely related to privacy, and the defamation of others is an invasion of its privacy. The rights to privacy in calculation includes the right to know, the right to participate, the right to forget, and the right to supervise. The right to know means the right to obtain privacy resource of different participants. The right to participate is the right and the methods to participating in the processing of privacy resource. Right to forget is the right to remove privacy resource from the DIKW graph. The right to supervise is the right to supervise the behavior of all participants in the calculation of privacy resource. The right to supervise is the first layer of privacy resource protection, and we call it as supervision mechanism. The supervision mechanism includes the logic supervision and the value supervision and the right supervision. The logic supervision is a supervision of common basic logical errors. For example, if the number of words is greater than the number of voters, this means there was a logical error. The value supervision is to supervise whether the AI system will lodge the value of privacy resource when it makes decision, and the right supervise is supervise whether the participant exceeds the limit of their right to privacy. As we can see, this is a figure, shows the direction. Now we can see this is a figure, shows the direction of privacy resource in the calculation. We can see that there are three participants: the generator, communicator, and the acquirer. The PDIK in the figure means privacy resource, and the different participant has different privacy rights in the different link of the calculation. In the third part, let's discuss the privacy protection methods other than the supervision mechanism. The first is the anonymity mechanism. It protects privacy resources based on their different types, stored in the DIKW graph. This is the data anonymity method. We can use the parameter A to represent the result of HIV test. The professional visit will know the relationship of the two dates, and he will not be affected. But for the hack, he is unable to check this password. This is the information anonymities. We cut off the relationship of the user and the privacy resource. For the doctor, he can get the privacy resource he needs for the research, while the hacker, he will know nothing. This is knowledge anonymity. We can see that the knowledge has an attribution, the validity. It shows the correctness of knowledge. When we hit the validity of knowledge, all of the related knowledge is the same for the visit. In these sections, the visit will provide different service based on the different knowledge, which can ensure the choice autonomy of user. The third method of privacy resource protection is to calculate the difficulty of transition of privacy resource as the Schur equations. If it's very hard to transition the privacy resource, the probabilities of leakage of related privacy resource will increase. But when we don't know the ability of visit, we are unable to calculate the transition difficulty of the visit. So we propose the third method of privacy resource protection. Like this, we can see the PDIK out is an attribute of every privacy resource. It presents the out degree and the number of new privacy resources that can be generated by this one. As we can see in this figure, the PDIK out of these pictures is 4. It can generate 4 new privacy resources by the transition and the association with others. When there are 2 privacy resources can achieve the same effect of the visit, we should choose the privacy resource with a small PDIK out, which can reduce the leakage of privacy resource caused by the transition. The above is all the content of my report today. Thanks for your listening.
The topic of our paper is defending use of the free via relationship between memory and the pointer. We will introduce our work from 5 aspects. Existing approaches to defending use of the free exploits are usually done using static or dynamic analysis. However, both static and dynamic analysis suffer from intrinsic deficiencies. The exciting static analysis is limited in handling loops, optimization of memory representation. The exciting dynamic analysis, which is characterized by lacking the maintenance of pointer information, may lead to loss that the relationships between pointers and memory cannot be precisely identified. In this work, we propose a new method called SC-GAT without the above barriers, in the aim to defending against UF exploits using fine-grained memory information management. In particular, we designed a key data structure to support the fine-grained memory information management, which can maintain more information to capture the relationship between
pointers and memory. Moreover, we design code instrumentation to enable UF-GAT to precisely locate the position of UF vulnerabilities to further terminate malicious programs when anomalies are detected. To understand the UF vulnerability more clearly, we categorized the UF vulnerabilities into 3 types. Type 1 allows an attacker to directly leverage the pointer that is allocated with a corresponding memory space to run, read, write, execute operations. This type of vulnerability is due to the lack of carrying out the nullifying of the pointer in time, which results in downing pointers. We state that type 1 is the most common UF vulnerabilities that may be easily exploited, and we show an example of the vulnerability of this type in Figure 1. In type 2, a pointer is obtained by pointer propagation. It has to rely on an exciting pointer which points to the field memory. For example, the pointer variable PTR is returned when memory space is allocated, but the value of the variable PTR2 is made identical to PTR by assignment. The UF vulnerabilities caused by PTR2 should belong to type 2. And type 3 enables the pointer to be obtained by directly calculating offset, rather than by using the exciting pointer, which has already pointed to the read memory. Type 3 vulnerability is typically exploited by combining multiple processing logic. Its exploitation may require the combination of other vulnerabilities, such as integer overflow and stack segment overflow. Let's introduce an overview of UF-GAT. An overview of our design is illustrated in Figure 3. The overview is based on LLVM compiler framework. The UF-GAT path in Figure 3 is realized by the LLVM path. UF-GAT participates in the compilation and linking process of the source code, so that it can insert the instrumentation code in the compared target program, and linking the compiled function library with a binary program during the linking process, and implement the instrumentation function to produce a protected binary program. Figure 3 is used to show the data structure for storing memory and pointer metadata. The pointer relationship between the memory and the pointer is established through the address stored in the metadata, which lays the foundation for the implementation of the subsequent instrumentation function. And Figure 5 shows the relationship between memory and pointers. The static instrumentation for our UF-GAT is implemented in the LLVM compiler framework. Therefore, the source code can be compared into an intermediate representation based on LLVM IR. In the compilation phase, we traverse each instruction in each function, pass all related instructions with pointer operations using LLVM-IR, and save the corresponding parameter and OP codes into the preset variables. We classify the parsed instructions obtained from previous step according to the LLVM-IR instruction set, and insert the corresponding instrumentation functions according to each instruction. According to the preset instrumentation functions in the compilation process of the static instruction, we design a runtime library for UF-GAT to fulfill the task of the runtime defending. There are 4 main instrumentation functions, known as create, press, check, and remove. The instrumentation function create is to build the information relationship between pointer and memory. The PTR is pointer storing the address of the memory that is allocated by the heap memory management mechanism. Parameter key is the size of the heap memory space that requested by users. The design of create is described as follows. First, if the value of PTR is null, which means that the malloc has not successfully allocated the memory, then we stop building the permission relationship. Otherwise, we build the metadata of memory block and the PTR data of pointers according to the value of PTR and key, and establish the relationship of memory data and PTR data in doubly linked list. Moreover, we insert the metadata and the PTR data into the enhanced read-black tree to accelerate the querying process. We use the memory address and pointer address as a case of metadata and PTR data respectively. To prove our effectiveness, we evaluate the defending effectiveness of UF-GAT over all types of UF vulnerabilities, and further test the well-known CVE vulnerabilities in multiple versions of programs, including Cross, Worksharing, and OpenSSL. Through the analysis based on real-world vulnerabilities, we can conclude that UF-GAT is highly competitive with the other runtime detection method. Regarding the overhead of compiling and the linking process, we mainly choose to compare with another method done now. We measure the change of the programs by counting the difference between the file size before and after compiling and linking. And gathering statistics for the instrumentation functions. The experiments counts that related information at compiling linking process for 16 programs, including 11 C programs and 5 C++ programs. UF-GAT requires the support from the runtime library with a size of about 390 KB, but we stated that but we state that this actual overhead is necessary for recording the pointer status so that we can guarantee the precise detection and defense over the UF vulnerability exploits. Regarding the runtime overhead, we made a study as shown at the table. We designed and implemented a Chrome plugin for UF-GAT, which records the result of accessing the legacy top 100 websites. The average time overhead of UF-GAT and DNL are increased by 21.9% and 21.7% respectively, which shows that both methods share similar performance on the average time overhead. The rendering time of the normal website is within about 2 seconds, and the actual time overhead is about 0.5 seconds, which is almost imperceptible to website clients. With the increase of download number, our UF-GAT perform better than download. In this work, we have proposed a novel approach called UF-GAT based on a design over fine-grained memory permission management with the aim to identify and locate UF vulnerabilities. We have also conducted experiments in which we implement UF-GAT on 64-bit Linux system and exploit it to transform a program into a practical version. The experimental results demonstrate that our UF-GAT overperform other exciting approaches in terms of detection, accuracy, and overhead. It also shows that our UF-GAT is able to effectively and efficiently defend all the three types of UF exploits. In future work, we plan to design an automated UF vulnerability discovery system for defending exploiting heap memory vulnerabilities with more description information of pointers. Thanks for your listening.
Hello, my name is Shuyin Ouyang, and I'm from Central South University. It is my honor to present our work, API misuse detection, based on stacked LSTM, on behalf of our research team. My presentation will expand from the following aspects. First is the introduction, and the second, related work. Third, the method. Fourth, experiments, and finally, conclusion and future work. Now we come to the first part, introduction. Nowadays, API plays an important role in software developing. The developers can save a lot of time to access libraries and frameworks via APIs. More and more enterprises choose to reuse existing data structures, frameworks, and class libs to complete the rapid development of new software projects. Although API reduce projects' development effort by accessing underlying services, it brings the challenge for ensure the correctness of programs. API misuse often occurs in the projects, which includes using redundant API, using wrong API, missing key APIs, ignoring the handling of exceptions that may be thrown in some APIs, which may cause defects or even serious problems. API misuse is an inevitable problem while developers are using APIs to develop projects. And generally speaking, API misuse is caused by the following reasons. There are lots of APIs, and usually an application involves various API interactions. For example, Java in Cache API is used to create a cache between distributed nodes, and the interaction between distributed nodes requires the support of a Java remote call API. Second, the quality of API documentation is not good enough, and the low-level documentation is the main obstacle to API learn and use. Third, API needs to be continuously upgraded and maintained, but the corresponding API documentation is not upgraded in time. Now, we come to the second part, related work. In this section, we review some related work in the area of API misuse detection. We simply divide the existing study into two parts, language models and the specification mining and the defect detection. First, language model is utilizing API semantic information from the existing method. It is very useful to applying natural language processing models to API misuse detection. But the localness in source code, which refers to the complexity of code structures, still is the chronic and the main challenge for API misuse detection when applying language models. Second, discover codes grammatically structured. The existing specification-based code defect detection method show great performances on analyzing structural information on real-world code. Therefore, learning API user specification is helpful for API misuse detection. Finally, we propose a deep learning approach based on a long short-term memory, recurrent neural network for API usage specification learning and API misuse defection detect. So we, based on the related work and our proposal, we finally choose to use the semantic representation of APIs and the static LSTM neural network to achieve the API misuse detection of our project. And now we come to the third part, the method part. There are three main steps in our approach. Now we come to the first step, static analysis. In this step, we design an API called syntax graph, which called SC-GAT for short, a presentation of API usage, which can capture the order between API calls and data interaction, which can distinguish misuse from the correct usage. Abstract syntax tree, which is short for AST, is a powerful tool to map the Java code into a tree data structure. We use the Java phraser to phrase out the structure of the source code as a presentation of API usage. SC-GAT is a direct, connected, multiple graph with name, node, and age. And the picture in this page shows an example of the SC-GAT in our paper. Now we come to the next step. The second step is called data generation. In this section, we design a new API called mining algorithm, which can generate all the API call sequence into previous API sequence and the next API form data. Through learning the API user specification, we apply word-to-vec as a pre-training model to achieve the representation for each API, which can make use of the API semantic features among the API sequences. And in the data generation step, we have two main tasks. The first is the API sequence mining and generate training data. In this task, first we need to build a vocabulary, which we store all the API informations. In our research work, we found and referred many API mining algorithms due to the fact that our SC-GAT is still a graph. So we designed an API sequence mining algorithm to squeeze the API call sequence among SC-GATs. The basic principle of this mining algorithm is to explicit the API sequence, which start with the in degree of 0 nodes and end with out degree of 0 nodes. And the second task is API embedding, which is important. And in this section, we use a model called word-to-vec. Word-to-vec is a kind of word embedding algorithm that provides a state-of-art outcome on various linguistic tasks. Due to the distributed hypothesis, which proposed that the words appear in the same context tend to have close relations. As a pre-training model, word-to-vec can present words as d-dimensional vectors so that words have close relations with others can have a similar vector representation. We treat the API call sequences generated above as a sentence in the task, such that the adjective APIs can be semantically embedded into the similar vectors. API embedding is a solution to the problem of numerical representing of APIs. And the third step is the model training. In this step, we can first see the overview of our model. Well, our model can simply be divided into 4 parts. The first part is the input API sequences with the form we mentioned in the data generation before. And first, we need to embed the API sequences. And after embedded, our API sequences became the API semantic representation. And then we put this data feed into the stack LSTM neural network. After learning and training in this neural network, we finally get the corresponding next API probability list based on the previous API sequences. This is our basic idea of this stack LSTM model. And the model we propose, the full name is called the Stacked Deep Learning LSTM Network, which is short for SLSTM. We present the LSTM model, SLSTM model, which takes the stacked input of a certain number of time steps to predict the output. Assuming that we have only one features, we can illustrate the concept of SLSTM as the figure shows in this page. Via embedding layers, the original sequence of input is divided into multiple stacks, which form the new input, and where the number of the stacks. Therefore, each stack we created can be considered as one new time step and reduce the temporal spaces of the model cost. Noting that every input stack consists of a fixed length of original API sequence, which is considered as a new input feature to feed in the SLSTM cell. SLSTM is not only reduce the temporal dimensional, but also represent the semantic meaning of each APIs in the previous API sequence. It is worth noting that it is an empirical number and depends on the specific embedding rules as well as the domain mode of the dynamic model response. In addition, LSTM observed to promote better training and prediction performances as compared with other models we shown in the section 4. Now we come to the section 4. Section 4 is the experiment part. In this part, we first will tell you something about the experimental objects. Java GCE, which is the full name is Java Cryptographical Extension, is a package provided by JDK, which can provide the implements of cryptographic primitive, including block, ciphers, and meshed authentics codes. Java cryptographic APIs provided by GCE are under the package named JavaX Crypto, according to related research, by separating the implementation details for the users. Developers can use it conveniently to achieve the encryptions and the decryption functions. Also, these APIs also provide multiple models and the configuration settings options. However, to use and combine this API correctly can be challenged for developers. In the following part, we will focus on the experimental object of GCE to illustrate the ability of our model in defect detection. It can be seen from the result that SLSTM is always higher than the other. At most time, it is always higher than other models. The recall rate of both models are very low, where they are in the top 1. But as the top K increase, their recall rate also increase. The overall SLSTM's precision is always higher than the other models. Since the model's recall rate is greater than 50, the model has defect detection capabilities when the top K is taken to be top 10. SLSTM defections works best, which can be seen from the SE score pictures in this page. And finally, we come to our fifth part and the final part, conclusion and the future work. In this paragraph, in this section, we will state our primary contribute of this paper, which can be summarized as follows. First is the static analysis by ACSG. The second is the API semantic embedding. And the third is the static LSTM for API prediction. And our paper proposed a deep learning approach based on the LSTM network for API user specification learning and API misuse defection detection. We designed a static analysis method called ACSG for presenting the API usage, different from the existing models of our proposed architecture at embedding layers, which applies the pre-training model named word-to-vec to achieve the semantic representation of each API in the sequence. The model we proposed named SLSTM. The capability of this model is illustrated in the experiments mentioned above. And finally, we compared the performances of the model with the existing models. And we finally found that SLSTM has better performances with FE scores 0.16172, where the threshold is among top 10. In the future work, we plan to verify our method in various types of APIs in order to demonstrate a higher applicability of our approach. Due to the natureness of the source code, model in NLP area with great performances can be applied into other semantic representation for API or API use specification learning process. This is the end of our presentation. If you have any confusion, please contact me as soon as possible. Thank you for listening.
Dear colleagues, CollaborateCom 2020 has come to an end. Hopefully all of you have enjoyed the conference. Because this is an online conference, all the presentations have been recorded. Please spread your presentations to as many people as possible. This will promote yourself and also promote the conference. Let's work together to make this conference better and better. Here, Hong Hao and I would like to express our greatest gratitude to all of you. Without your participation, it won't make CollaborateCom. We would like to thank our sponsor, EAI, for their continuous support of this conference. We would like to thank the organizing committee for their time and efforts put on this conference. At last, I would like to personally thank our technical program committee team, led by Professor Hong Hao Go. They have worked day and night to have all the papers reviewed and decisions made. They have made a wonderful program. Without their hard work, we won't have such a successful conference. I would like to thank our conference manager, Carolina, who has coordinated the whole team to manage the finance, presentations, and the conference a success. I would also like to thank our keynote speakers, whose high profile and excellent presentation have added tremendous credit to our conference. As a tradition, I will make an announcement of the best paper and best student awards for this conference. The best paper award goes to the paper Forknot, Pairwise Active Learning for Intensive Cell Image Segmentation. This paper is authored by Lin Bo, Deng Shuiguang, Yin Jianwei, Zhang Jindi, Li Ning, and Go Hong Hao. The best student award goes to DEX, Collaborative Edge Data Storage Service for Edge Computing. This paper is authored by Fu Xiaozhou and Hou Pengchen. Let's congratulate them on their success. The second announcement that I'm going to make is that we are going to organize a special issue with general mobile networks and application to support this conference. So we are going to keep you informed of the progress by email. So please try to submit your extended paper to this special issue. For all the authors from this conference, have got high possibility to get your paper accepted. Please also submit your extended paper to EAI Transactions on Collaborative Computing. This journal is designed to support our conference as well. At last, I'm going to announce that CollaborateCom 2021 will be held in Suzhou, China next year. So all of us in China know that Suzhou is Paradise City of China. It's very, very famous for its long history, its gardens, silk, lakes, delicious food, Suzhou Opera, and ancient villages in and around Suzhou. There are more and more you can see in Suzhou. It is a very good place for conference and also for family travel. So hopefully all of you could join us next year in Suzhou again. So see you all next year in Suzhou, and thank you all.